Right, hello everybody, welcome. How are we doing? How are we all doing? Welcome back to another stream. Right, so today's just get my levels right. I took a week off and this all feels weird again. But yeah, so exciting day today. We're starting on our new project today, which will be running a game without an engine. So I've gone and set up a minimal repo. I've got a README and a license in there. So we're literally going from scratch today. Yeah, man, it's gonna be an exciting day. So we've got quite an ambitious, got quite an ambitious first stream. We want to try and get a compute shader running. So it includes getting a window open and setting up Vulkan and run a compute shader that consistently runs, right? So we're obviously going to cut a lot of corners, but I think it's possible. We also already have this code basically written in my old HCC project anyway, but we are going to be going through it step by step and going over everything that's involved in that. So yeah, it should be good. Hey there, Ransel. Yeah, man, it's a lovely logo. You see, with that logo, I took the 3D voxel ray marcher that I had for the HCC logo, and I basically like modified it to work on. Yeah, so I modified this one, basically. Yeah, with the Hero Dev logo that I got now. So yeah, it's cool. Hey there, Kairu Ken. Welcome back. Hey there, Joker Dan. Welcome back too. How you guys doing? Yeah, so for those who don't know, we're building a game without an engine, purely because, what should I do as a quick spiel for this? So yeah, for those who haven't seen, we've been working on a project called HCC, which is C to Spear V compiler, and I really want to test this thing out, so I could go and build a whole big engine. But then I'm just building an engine for sake of building an engine. So the idea is we really want to test it on a game as fast as possible. So we want to try an approach which I haven't tried before, which is just building a game without an engine and just building, you're still building like engine code, but you're building it straight into the game project itself, and you're not gonna. The idea is to think simply and solve your problem that you're solving and not try and oversolve it with a general solution, which is very easy to do. It's pretty much my default way of thinking. So I want to try and turn that part of my brain off, while we try and do this thing, Good, hope you're doing well. I've been here for a minute. Essentially prototyping. Yeah, you could say that too. Yeah. Like you just build the systems you need. Don't try and overthink it. But yeah, we are prototyping the first stage of this. That is true. So we are trying to find a 3D art style. So we're not going to go with a traditional triangle rasterizer. We're going to do something different, which will be revealed as we get there, basically. And we want to try and find that first before we start thinking about what is this game. So we're just going to get the essentials to get graphics going. We'll get some keyboard input so we can have a bit of a play, get some basic UI so we can change some values, and get some hot code reloading so we can recompile stuff and not have to keep restarting the game. Basic stuff like this. And that is the plan. So, right. What do we want to do first? So we just want to start off by getting a source directory. That's essential, right? Probably get a build directory as well. What other things I typically like in the root? We won't really need too much. Probably a third party, because that's where our compiler is going to go in there, and other things. Yeah, so I think we'll start off with that. So yeah. Also, if you guys are subscribe to Twitch or support via Ko-Fi, you'll also get access to this code as well. You'll be able to download it. There's links on the Discord basically. Where I'm completely forgetting my commands I made. I made some commands. Let's get these commands up so I can just there's Discord, right? Code. There you go. Yeah. Right. So all the info is there for those who are interested. It's not everyone's thing, but Joker Dan's got it as well. Excellent. Yeah. There we go. Right. So if you are following along, we expect to have your Clang compiler installed. We are doing the Linux side of things today, but if you're on Windows, maybe you can just do the Windows version of it. It probably isn't too difficult. Just a bit of googling, but we will be doing the Windows version. Depending on how far we get today, we might do it next stream, or we'll so we'll just switch between Windows and Linux as and when it makes sense. So yeah, that's the plan with that thing. We basically need is Clang installed. We're just gonna do a simple build script. That's another directory I forgot. I need a scripts directory. We just dump all our scripts in. So our directory currently looks like this. We've got a build folder, got scripts folder, source, and third-party folder where we're going to stick things like the HCC compiler, maybe the Vulkan SDK goes in there as well, and any other things like maybe STB image or stuff like that. Cool. Hey, very much. Oh yeah, here where it started. I remember you discovered me halfway through when I was making HCC. And it wasn't at a point where I decided to, where I had the resources done at that point, was it? It was still kind of like half. Yeah. I think I just finished writing most of the C language part, but not writing any of the graphicsy side bits of it. I remember that. Hey, perhaps. Oh, my days always. I've taken a week off and I've forgotten your name again. How to pronounce it? Hats, exit, something like that. Solvent told me about you. Excellent. Yeah. Yeah, Solfam. Hats, exit. Good. I got it. Right. Okay, so how are we going to start this? So basically it's going to source directory. Let's just get a couple of files in here. We want to probably have a main.c file, right? We probably want to have a core, core.h, core.c. These things are going to have all of our core utilities in. So like custom memory allocators, custom memory allocators, custom collections, time utilities, memory utilities, just anything that's like your essential building blocks of the game, essentially. But they're not the game itself, right? Then I think we want to have a couple of operating system layers where we'll have like an interface. Maybe it's like open file or open up a window. And I think we'll have a file for each operating system that implements this interface. That will essentially compile out depending on the platform we're on. So that way we can just implement it in a different file for a new operating system, and it keeps it all in different files, which would be nice. It has its pros and cons, but we're going to try it this way. So we're going to have an os linux.c, and we have an os windows.c. I think those are the files we basically need to get a window open. Like I could go more, but that'll just be overthinking it. Yeah. AFK getting ice cream, nice. Tell me what flavor ice cream you got when you get back. Love a good bit of ice cream. Yeah, so you could put this all in one file and put if-defs everywhere, but then, yeah, there's pros and cons. Like sometimes if it's a Unix operating system, they're basically the same thing, and you're copying the file and duplicating the code, but then it's clearer when you read it. So yeah, pros and cons. We're just gonna do it this way. So let's start simply, and let's just open up main.c, and let's just get a main function, do the classic hello world thing. So I'm going to use neovim here, int main, in argc, so it's the number of arguments that come in through the command line, then char star star argv. So we're just going to return 0 and include, see, now this is something I want to try and avoid as well. I want to avoid including any yeah, I think yeah, we do have to use a standard library, but I think I want to try and not include any standard library stuff in header files, and maybe avoid it, maybe only keep it inside the operating system compilation unit. So in the OSC files, maybe. We'll see how that goes in the end. So let's just include standard IO here. We'll probably just get rid of it. We're just going to say printf. You do the classic hello world, right? Just to show that we've got something compiling. So I'm just going to open up in that scripts folder that we've got off the root directory. We're going to add a build.sh. So we're just going to stick with a simple shell script right now, just because using systems like make and cmake, they have their own complication, and we're just going to have like a few files to build, so we might as well just hand write it. In the future, we probably want to write a custom C program, which would be very minimal and designed specifically for our projects that would just compile this stuff. But for now, this is the most simple solution that gets us going. So you can just type clang-o for output. We're going to output a main, or in build / main. Well, no, we'll call it game, right? And then we'll say in source / main.c. Yeah, so we also want to run mkdir, which is make a directory, do a -p to say that we don't care if it already exists, and do a build. Something like that. Now, if we open up a new terminal, we're going to then run the build script. I think I might have to give it the right permissions. So I'm going to say chmod a+x to say it can be executed. And there we go. So now I can execute this thing. And there's no problems there. So now we should be able to simply run build. And there's our game, hello world. Cool. So now the next step would be, let's interface with X11 and let's get a window open. And let's probably have a main loop that we can then close the program from as well and handle those sort of things. So you'll notice we're only compiling the main file here, main.c. But we went and made an OS Linux, OS Windows .c and a core as well. So you can invoke Clang to compile these files separately into these things called object files, which are .o files, and then compile and then link those together into an executable. But that's just kind of extra effort. And our code base is very small. So the most easiest thing to do from here right now is just include them all into the main C file using include and just have one compilation unit. So to do that, all you simply need to do is include them as if you would include a header file. So we're just going to include os linux.c and os, we'll include, core.c, right? So that will compile those files as well. It simply includes them straight into this file. And this is a technique known as a single compilation unit. It has benefits because the compiler, like when you evoke this version of Clang, when you evoke Clang here on this main C file, it will have, because it includes all the other files, it can clearly see the source code across your whole program, and it can then bring optimizations in quite easily across your whole program. But the downside is you don't get to sort of, if you have a large code base and you're only changing a single file, which is maybe like 1,000 lines of code, like you don't get to like just recompile that module and then just link it all together at the end. So there's pros and cons to this, but again, our code base is small, so this is just the easiest solution to do. So let's just roll with that for now. Cool. So the next thing to do is we want to open up the source. os.h. Now with header files, you kind of want to use this thing called pragma once. And this basically says, if you include this file more than once, it won't, after you've included it the first time, it won't include it any more times after that. So it will save essentially copying and pasting code into the same file more than one time. The old-fashioned way is to do ifdef, if not defined, and then you define a macro. But yeah, this is just supported across all compilers, so it's pretty much good. So what sort of interface do we want for this? So I kind of have done this before. In HCC, we have a sample program. So I just want to shoot over to there and just take a look at that sample program, because it's a good, I called it DM for display manager. So this could be a good starting point, but yeah, let's just take this and then just modify it for our needs. So we're going to call this OS event type. There'll be an unknown event type, which would be 0. It doesn't conflict. Oh, linters, what are you doing to me? Right, I think my linter is bugged because I need to copy, where's those? I need this Clang D thing here. Because I need these in the project. Because it thinks it's a C++ file, but it's a C file. Right, it's because C and C++ use the same header extension. Like it allows struts inside struts. What is that union thing inside? Yeah, so essentially it's an anonymous structure. So it's as if it's the same thing as if I was to declare a union. Right, so a union is like a structure, but except for every field overlaps. Yeah. So a good way to explain this would be, imagine if we just did this and said union test, right? And then instead of putting the union there, we did test. Well, actually, no, we couldn't do anything like that. Right. These two things are the same thing, right? This is the same as doing this, right? Bear in mind, you do have to type def this. Yeah, you do have to type def that, but it's basically the same thing, right? These two are the same thing. But the benefit of doing it this way means that when I have this DM event here, I can say event.key, right? And although it's even inside this union thing, I can still say .key. I don't have to say .test.key or anything like that, right? It's called an anonymous union or anonymous structure. Hey, Paya, welcome. Thank you so much for the sub. Appreciate it. How's things going? Yeah, yeah, like those Reggie emojis. I'm excited to get those in. Those look good. Just gotta copy those. Thank you so much for doing them. They're awesome. And then also another thing with a union. A union, basically every field overlaps each other in memory, whereas a structure, this is like 4 bytes, and then this union will sit after those 4 bytes. Whereas if it's a union, each field of the union basically overlap each other, and it could be any one of those. Right, so that's the idea. So I've got myself in a bit of a pickle. I need to close everything. And right, so I've got these new Clang deconfiguration things. I've said turn that off because there was a problem with that. I remember trying that before. And all these compiler flags. Right. Yeah, so this is the flags it's going to invoke it with when it's using the Clang D language server protocol. So it should remove the C++ errors and stuff like that. So let's give that a go now. So I've just put that in my root of the directory and with my neovim set up. That should be better now. Anyway, back to doing some... Right, unused parameter, that's fine. We'll sort that one out. Where was we going? Oh yeah, os.h. Hey there, not so red. How you doing? Appreciate it. Yeah, I'm 6'6", aka vertically fat. You know, I'm horizontally skinny, but you know, yeah. But, yeah, C++ mode. If you have any other language in your message that shows up, not just any other language, specific languages. You just have to find them all. Yeah. Afternoon day. Welcome. Awesome. Yeah, I'll be posting these up on YouTube as well. The VODs will go up on YouTube, plus they stay on Twitch for a bit. So if anything is missed, just hop up on there and watch it. I'm also hoping to do some sort of some videos every so often where we basically recap what we've been working on in a very short form way. And they've got these long form videos as well. But yeah, doing good, not so red. Hope you're doing good. Awesome, you're doing good. That's cool. Yeah, hopefully we can get a pixel up today. That's the plan. We're going to go over everything it takes to get a pixel up using compute shaders only, including doing the basic X11 windowing. Dash pedantic, the same as dash W. I think it is. Yeah, I think it is the same. Yeah, it sounds about the same. It basically means we want to stay within the C standard, no extensions, right? Yeah, right. So we've got these like uint32s here, T's. And since we're doing a game without an engine and we're going to own basically the whole project, why don't we just shorthand this to U32 or something like that? And that's what we're going to actually do. But let's just correct all of this quickly. We'll have a window. Right. Operating system initialize, operating system window open, process events. And this is basically an iterator where we just say while this is true, while I have events I'm going to process these events, and then you go through all the events, and when they're finished, it returns false, right? Right, we've got to get our code in order here. So we're going to include a core.h file. So this is another one. We'll come back to this file in just a bit, and I spelled tab new wrong because I was... Right, there we go. So again, because this is a header file, pragma once, plop that in there. Now, we want to try and avoid using standard headers. We could just include standard int.h. That's typically fine. It's probably okay. Yeah, it's probably okay. Let's just include standard int.h, and that's probably our exception to the rule, right? So we're just gonna, like, we can always change this layer. So we're just gonna type def like this and do some shorthand versions. Just because typing those is effort, and it's our own code base, so we might as well just make it easier to use. So we're going to have our classic unsigned 8-bit integers all the way to 64-bit. So we have our size integers, we have our signed versions, like so. Then we actually also want pointer-sized ones. U pointer, S pointer. So this is when we're dealing with like addresses of things. We want these guys. It's probably some more like the mins and maxes of things. But yeah, we don't quite need those yet. And you probably would stick stack asserts alongside these, but let's just start there. So include in our core file now. And now we should just be able to use our shorthand U32s like so. See, we returned int here, probably because I was being lazy. And this is taken from a sample program, isn't it? So, so if we include the HCC stuff, we could return vectors of things because we'll have our vector types from there. But yeah, I think we don't necessarily need the display dimensions. Yeah. Let's just open up a window and we'll pass in a U32. And we'll get back this. See, what's the best thing to do? Should we give back 2 pointers to represent it? Probably not a good idea. So I think here it might be good to have like a window ID, and this is like a little 32-bit integer handle that we're going to use. So I think, why don't we define something in the core, and again we'll sort this thing out, but I think I want to say like core or define, or like handle define, and just give it like a name. So what is the name of this handle? And I think we want to do like a wrapped type here. So just have the name of the handle, and then it would just essentially be something like, so this is going to be a pattern we're going to have quite a lot, is we'll have these IDs or handles, as we're going to call them, and it's just a wrapped integer of something. So we'll just call it raw, like that. Get rid of the semicolon right there. So you do want to call that a handle, because I can call that a window handle, but the handle's a bit long, so I typically like the name ID. Core ID define, something like this. Yeah, so then we'll say like core ID define, and we're going to say OS window ID. So we're going to use this in quite a lot of places. Just save both and that'll correct that. Nice. And this is what will get returned is just a integer, basically. But it's wrapped inside of a structure, so it's a distinct type. And it's type safe. So we'll pass in a width and height we want for this window. And then we get back this handle for it. So if we want to do anything with it regarding this window in the future, we just pass in the handle. And Boolean, we don't have Boolean. So I think another exception to the rule is we can include standard bool, because I think typically these headers are basically very thin and they should be okay, even though they do vary across operating systems. I think they're fine. So we'll trust those ones. Cool. Right. So as we add more functionality, this will be split into different sections, but for now, this is good and we can start using it. Hi Perry. How you doing? Good to see you. Welcome to the stream. I love how Perry is new and is somehow a moderator, you know? It's like he's hacked the system. Hey, Kulama. Remember catching my streams during COVID times? So no Perry. What do you mean Perry was here COVID times? I'm pretty sure. Perhaps I'm misremembering. Excellent. So now we want to fill in the... So remember this is like an interface and we'll fill it in specifically for each platform. So we're going to have a OS Linux. And this is an implementation here. So what we want to do is simply just copy these and implement them. Now, yeah, OS initialize will do nothing. We technically don't need it, but oh well. Open a window, process some events. And for this one, we're just going to include the operating system header. Sweet. So basically, we want to have some form of right. I think I might want to make another header file because I like header files in C, and it's kind of they're a good way of looking at the code base from a zoomed out perspective, so you can see like the data structures and just the functions and not all the content of the functions. So something that I like doing, even though this stuff is only going to be local to oslinux.c, is I like to make an internal header where it just has all of the internal structures and functions which are specific to the Linux operating system file. So one, you can include it into another file if you just want to hack something together and then remove it later. But also so you can just look at the header file and see the internal stuff from a zoomed out perspective. So I do kind of want to make one of those as well. But again, we're not going to have too many files in comparison to other projects. Our files are typically going to be thousands of lines of code, pretty much always, except for a few headers. So we're just going to say, we're going to write the word internal at the end, just to specify its internal header. And why do I want this? It's because I want to have some form of like internal See, unless I don't have the management of these windows, you know what? We're kind of overthinking it here. Let's just not do this. let's not do it. Let's save it for later when we have the problem. So for now, we're just going to return the 0 handle, or a handle with 1 or something like that. So ID equal 1, something like this. So our handles typically want to have core ID null. So all our handles 0 means, all our IDs 0 means null, I guess. And we'll just return that. We're not going to be opening multiple windows for a long time, so this should hopefully do. Perhaps we can have like a static int here, where we say like times called equals 0. And we'll just do an assertion here. Now we don't have an assert here, so let's write that as well. Core assert. We want to say times called is going to be equal to 1, 0 rather. And we're going to say like, you know, multiple windows it is unsupported at this time. And now this is where we're going to write the code to actually initialize this X11 window. I'm going to move back to work tomorrow. How's the time of streaming? Yeah, time of stream was good. Like, I had a nice time just chilling, and I played a few games. Prepared for the baby, got some baby stuff. You know, went outside, had some walks. Had the niece and nephew over, looked after them for a bit. Saw the new Guardians film. You know, just relaxing. It was all good. Actually prepared now. Probably not. We still need. We got little Moses baskets so the baby can sleep in it, but we still need to get a car seat so we can actually take the baby home. If not, the baby stays at the hospital. But we ordered one, and then Amazon like mysteriously cancelled it. So I'm waiting for them to refund me, and then I'll buy it again. So yeah. Hey Glass, how you doing? How you doing? Just gonna open up a window quick because it's getting a bit warm. No, I didn't order a baby. Unfortunately, then on next day delivery. But yeah, that's a good point. OS Linux Wayland Day. Yeah, I don't know if I want to do Wayland. X11 is good enough. But potentially, it might be a good thing to do in the future. I don't know why. See, not many operating system, well, not like Linux is the only operating system that has 2 display managers. So yeah, we're just gonna stick with one. He's still a joke. Yeah, Prime delivery. Yeah, ought to be good enough. Hey there, Gabe. How you doing? How do you plan to keep state in the GPU? Like, do you say, for example, position of player in the world? You don't keep that on the GPU. You upload it basically. Like, if that state changes all the time, you either upload it or you keep it on the GPU and you update it via shaders. But yeah, you keep it in a buffer somewhere. Yeah, so that's one of the reasons why I don't want to do Wayland. I've never developed for it, so the X11 is just what I know best, and it just still works good enough. So Yeah, let's get these assertions in. So, right, let's hop over to the HCC project, and let's go and nick its HCC internal HC asserts. Excellent. Right, let's nick these guys. Get in here. So an assertion basically, if it's false, if the boolean is false, it will obviously crash, and it will tell you why. That's the basic idea. So we're just looking in the Hero C compiler project code base, because we've got them in here, and I've already thought about them, and they're awesome. So we're taking these ones. So basically, we're going to have these things called debug assertions. Let's get a header. Let's get a header in. Abort and assertions, sort that out. So abort is basically assert false. It just crashes, right? It tells you why, file line number. You get to pass in a message as well. You also have debug assert, which turns off during in some form of release build. These are some common ones like debug assert, non-zero, array bounds, array resize, power of 2. Cool, so let's just swap out these HCCs for the word core, and then we'll be back on our way. Meow. Right, so now I've got those buggers in. Oh, wait a minute, we didn't implement these functions. So this is a function as well. Let's just quickly grab that. So notice how we've got this no return here. So this means that it won't care about the return value. It will like if you stick this at the end of a function that has a return value, the compiler won't complain to you. Or if you have it in a switch case, where every other case returns and this one doesn't, it won't complain either, which is kind of handy. So we want to swap out those HCCs for the cores. So we've got our first core functions here. Let's just get these guys in. Source core. And we're just going to go into HCC core.c and nick those guys. Abort. Let's put them under the same sort of header. Core abort, core assert false, sorry, assert failed. So these obviously need to include the core.h and probably include the standard IOs, stuff like this, because we're just going to print out. I need VA arg, something like that. Standard arg, gotcha. This also has some stack trace functionality, which is super handy. So this means if you crash via one of these assertions or aborts, it'll do a stack trace. So we do kind of want to get that in here. So I was using this library called bstacktrace because I did have this implemented before in one of my previous code bases. But I found a single header library on the internet. So if you search for bstacktrace, you will find it. I was looking for a single header which did stack traces in C. So we're just going to go ahead and grab that one and stick it in the third party side of things. So Let's just plop that one in there. Third party. So we're just going to then include that into here. I think we need to include it with a, yeah, with this define here. Not found, eh? Okay. So this will be in our third party folder. So we should be able to do that. We've got to adjust our compile flags to get this to work. If I change my .clang d, no, that one, .compiler flags, we'll do a dash I for includes, and we're going to say third party, ./third party. Right. So we try that. There we go. So it likes all of that. So if core abort, let's get rid of these underscore prefixes. I'm not really a big fan of those anymore. I used to use that as mini internal, but yeah, I don't really care anymore. Cool. So how do these things work? Well, it just essentially prints into standard error abort. It uses this varargs thing to capture the variable arguments and throw that into a printf, and it's going to print out into standard error. Then it's going to print out the file that we pass via the file unline macros, and then it'll get a stack trace with that single header stack trace library, and then it'll print out the stack trace as well. And then the assert basically works the same way, it just prints out the assertion failed and passes in the expression which actually failed and prints it out. And how we do that is, if you look here on the assertion, here's the condition, and this is when we say if the condition fails, then actually fail. But so you've got the stringify here, this little hash for this argument means it will turn into a string, and it will just turn the whole piece of code into a string, and then you'll be able to print that out into the terminal, which is super cool. So I can just show that literally in a second. We'll just get this thing compiling again, I think. Good place to get it compiling again, I reckon. Where's these likelies and unlikelies come from? Let's get these as well. Core. Excellent. Let's just get those in there. Right, so I think we got to a point now where we've changed the code enough. We're not going to quite get our window open just yet, are we? But we've changed the code enough and brought some things in. It's probably best to adjust our build script and just show the assertion side of things and see what that actually looks like. We do want to have a... We need this unused thing as well. So we've put this, the extra command line, the extra -w extra on, and we've put -w implicit fall through, which is really good, and float conversion. So extra basically enables a ton of extra errors, or a ton of extra warnings, but we've made them errors with -w error. All warnings as errors, that's what that means. So one of the things that's in this extra is unused parameters, unused variables, which can be a bit annoying, but it does end up, when you're refactoring stuff, it really does help out sometimes, and it can be the difference between you spotting a bug and not spotting a bug. So it is beneficial enough, because you can have the assumption that you've refactored it right, and you'll just be assuming that you've used this new variable somewhere when you actually haven't. We've got implicit fall through, which means if you're using a switch case and you don't put a break there, it will be a compile error. Super good, super good. We'll probably see that sometime soon when we've got the event loop going. And float conversion, so if you convert between floats and integers, it has to be explicit. Again, which is nice because in C you can create lots of extra instructions by not knowing about it, basically, when you're doing these conversions everywhere. Awesome. So let's try and get this thing compiling again, since we've just brought a lot of extra awesome utilities to see how these guys work. So we're going to open up that. Let's open up that scripts. So we're going to make an argument, or a thing called, I think you say this, right? Flags equal, and I think I can do string like that. I think shell scripting languages are absolutely horrible. But yeah, it's the simplest thing we have right now. Like typically I'll make a simple C program, but this is more simple. So this flag means that we want to error if we use any C extension, it will complain. You kind of need these things programming on Linux when you touch the operating system, unfortunately. You basically say using GNU's version of C, but we're kind of not at the same time. Warnings as errors, float conversion puts it fall through, -wx we just explained. G means we export the debugging information so we can look at it in a debugger, super good. We link with a mass library, we link with a dynamic loading library, and use pthreads, which you can't escape, unfortunately, in Linux. Pthreads is when we do multi-threading, but you kind of need it when you use X11 as well, so anyway. What I want to add to this, I needed to add a -L for, a -I, wasn't it? For that third-party folder. Yes. And then I want to put the flags in here like so. Flags. So hopefully this works, you know. So something I have got in my config in my NeoVim config is I do have a thing where if I press F5, right, it's going to save everything, and then it's going to call this make thing. Run this make command, and make will run anything that is a make program. And I've set up my make program. Where's my make program? Yeah, my make program is running is going to run that build script we've got. So if I just press F5, basically it's going to run that build script. So that's what I'm going to be doing from now on, is pressing F5, and we'll see it pop up in Vim. So here it is here. It's in there's some unused parameters, as our language server thing was saying. And so we're just going to correct those now and get this thing compiling again. Hi, hey there, Tinspin, how you doing? Welcome back. Did you spill the beans on the project gameplay yet? No. We're going to be spending the first... We're going to just be focusing on finding a finding a 3D art style that we want. See what are the possibilities with this 3D art style that we're going with. We're not going to be doing a traditional triangle rasterizing or anything like this. So it's completely something different. So we're seeing what pros and cons this gives us. And we're going to, after we've discovered that and settled on it, then we're going to think about the game. What is this game? How much time do we want to spend making this game? And, you know, get all the factors, you know, think about what games I've been enjoying, what sort of game would I want to make, and yeah, that will be after we've done this research and development phase. So I'm going to use this not HCC anymore. Is this? Wait, did I change that? Oh, I didn't change it. So this macro here, just cast it to void, just basically kind of uses this variable, but it means it does nothing. It's weird. It's C. It's a C weirdness. So we're just going to say width and a height here are technically used, but we'll use them in a second when we actually make a window. And then we'll use this E thing here as well. So that gets rid of the fact that it's unused. We just return false here like this. Okay. So I press F5 now. Just got a couple more errors, which is argc and argv. And we just want to do the same thing. Here. argc, argv. Right. So we're going to print out hello world. And then we're going to call core abort. And we're going to say like, oops, right? World's worst abort message. But now you'll be able to see well, you know what? Let's put it inside of a function. Imagine we have a function called test, and we're going to now abort from within test. Right, you'll see that we've got stack traces, and we can kind of see exactly where that's going on. So if we build this, we've now built the game, then we're now going to go into the build directory and run it. We've hit this abort. It prints out oops. Obviously more stuff can go in here, but it's saying in the main C file line 7, so it's done that file and line stuff, because remember in the abort thing we passed the file and line. These are the built-in file and line macros, and then all the arguments just get passed into here, which is this function that we made, which we saw earlier. And hopping back to here, so there's a file and line get printed out. Then we're using that B stack trace single header library, which does an implementation for each operating system and gives us a really nice stack trace. Gives you a function name and it gives you a line number as well. So the only issue I have with it is it includes itself inside the stack trace message. I have written these things before, and this is typically noise, right? It just gets in the way of you being like, what function actually crashed? So notice how we called abort in here in this test function, and it's here, right? You can see it, line 7 test. And then it's called at main 19 at main 19. Yeah, the line number's a little bit off, but yeah. I think that's the best it could do with the debugging information. Well, that's where the instruction pointer is, or something like that. After it's executed this call, so it'd be down there, something like this. It's weird. But yeah, so I think what we should do is we should go into this B stack trace library, take a look at its interface. If it hasn't got the interface that we want, we'll change it. And we'll get it to remove these. Look at me, TensorFlow noise. Yeah. Not sure I get the joke. This is an AI joke, isn't it? Not sure I quite get the joke. You might have to explain to me, Machine Knob. But hey, welcome, Machine Knob. How you doing? Good to see you. Because of macros, no. No, I don't think that new line is because of the macro. Extra line is because of the macro. All this extra stuff is because of macros. But yeah. So we want to hop into the third party thing. Now we have changed from the default one, so how this thing works, so he takes void in when I've implemented these in the past, because I have done my own one, but I kind of like lost the code. Well, it's probably somewhere, and I was in a rush and I was like, there is this thing and it's cross-platform, So I'm going to use this, and it's, you know, complete, all in 400 lines of code. This is the type of stuff I like, right? So, but it doesn't quite do the thing I want to do, but it, you know, it's in my thing, in my project. So I am just going to probably just change it, right? So we want to stop it after so many, we want to say like, how many functions do you want to get rid of from the top? Right. So we want to say like ignore top count, right? No, U32, right? Okay, we'll do an int. Okay. So there is a toString here as well with some stack trace handle. That's probably going to have to take it as well. So you get the stack trace handle. We'll see the implementation of this. That's the Windows one, isn't it? No, it's not Windows. Don't know which one this is. Right, so this one's Linux, backtrace, depth. Yeah, so it's the toString one which needs it. Trace size, excellent. So this is going to be easy. We'll just take 3 off that, and it should do the job for us. So this thing here obviously needs it there as well. And we'll go ahead and adjust these guys. Wait, not toString. Sorry, wrong one. Which one is it? GetString. Which one was it was looking at? Was it toString it was looking at? Oh, there's multiple versions, right? So this is on Apple's platform. Yes, it's going to be a bit different. Each of these. Yeah, we can suss that. So it's just on this toString. Alright, I got this. CPP. C++. How dare it be in my code base? But yeah, no CPP here, which is good. Far more simple this way. So we need it on this get. Got it on the get. Alright. So this is the Windows one, is it? Yeah, D word, Windows. Right. So it's got the data, the entries as they call it. So entries plus I, then it increments I, because that's what post plus plus does, right? So it gets the current one. Now I here, can we get the number of entries? Where's the number of entries? It stops when what? Does it stop when I reaches something? Right, so it basically has a null one at the end, right? Which is not helpful. So when it does a get, so maybe the best place is to do it here. Yeah, it puts a null one in at the end, right? When you equal to the max depth. So what would be nice is if we just ignored it from here, then we don't change the other function. So we do it on the get instead. Yeah, maybe that's better. So rather than changing all those, we just change it on the get. All right. ignore top. So on the Windows side of things, and I've got to test this obviously in the future, but anyway, there'll be an I that's incremented, and until you reach, if I is equal to max depth, it will stop. I guess it zeros everything. So it's a malloc, so it's uninitialized memory. Mem set it. Where's frame? Stack frame set 0. It does this walk thing. Walks the stack frame, sets them up, and then it can return a 0 itself. So I guess the idea is it does return 0. So we want to get a count here. So we're just going to do int count equals 0. And effectively, we are going to say count plus equal 1. And then we just want to do this, right? So it'll be indexed with count minus the ignore top count. So if it's, and then minus 1. So it's indexing from the back, right? Now, what is bad about this code? Well, if the ignore top count of the stack is bigger than the total stack itself, it's obviously gonna go below 0, and that could go negative if it's signed, or it can go really big if it's unsigned. So that's not good. Typically I solve this with a min or a max side of things. Yeah, so we probably want to get those min and max. Yeah, where's that one? Min. Oh, these are good. Oh, these are all good. Let's get these pointer and number utilities in. So these guys, yeah, let's explain these. Oh, these are all good. Bring them all in. All right. All right, I love these things. Let's explain them. Give that a quick rename. Excellent. Excellent. Right. So we've got these core min and core max. So that just mins and max. Like this one returns you the min of A and B. This one returns you the max of A and B. There's a clamp where it takes a value and make sure it is at least minimum or maximum, in between the minimum and maximum range. Yeah, I know, Perry. I know. Being lazy. This unused one we saw earlier. Let's just delete that actually. Nice. So obviously these cores and mins are not great if you put like a function call in there, because it'll do the function call twice, right? So you have to be careful about that. Kind of not great about those, but just be aware about it. These ones round up to the nearest alignment, which is so useful for doing memory allocators and everything. They do some magic with the fact that it's a power of 2 and it's base 2 encoding for integers. Yeah, if you know your like how the AND operator works and these things and the format of integers, you'll understand how these work. So this round ups the nearest alignment. So typically you round up to the nearest power of 2, power of 4, that sort of thing. And sorry, not power. Sorry, the nearest round up to the nearest 2. Nearest multiple of 2, nearest multiple of 4. With these guys, and there's also a round down as well. Array count. So this just gets the array. How many elements in a classic C array? Check if something is a power of 2, add to a pointer. Yes, so these ones are really handy. I like these. So you can like, rather than just call memset each time, I have like a zero a pointer basically. And then I also have a way to zero a whole array or zero an array of things. I use these so much, and a way to sort of compare arrays and compare elements and stuff like this. So they're just shorthand utility functions. So yeah, that's just a brief overview of what we just dumped in the code base. I take these everywhere I go, basically. This probably can add some more, but they're the core things. Right. So what was it doing this? So wait a minute, I've gone and added these in, but I can't use them in btrace because it's a third-party library. Okay, I'll just do it manually. So we want to essentially we'll work out the last index, right? The last index is going to be if count is less than ignore, then we want to use count here. If not, we're going to use ignore count. So this one is going to be initialized to count itself. Then we're going to say take away equal whatever that is, and then we'll take away 1 at the end, and then we'll index into the back of the. Wait a minute. It's one too many, isn't it? So ignore 0, ignore 1. Wait, you don't need to take 1 at all. Yeah, that's it. Excellent. Right, so that will clear it to 0. Cool. So that's the Windows one implemented. So let's get the Linux one. Let's get the other platforms implemented. So this one is Apple apparently. Right, this does it. It does a stack. It returns a stack trace size, right? Excellent. So again, it'll be the same sort of thing that we saw. We kind of want to take away take away the ignore count, isn't it? Like that. Cool. Next one will be probably the same because it's Linux and it's Unix. Yep, that's good. So we'll do the same sort of thing again. And then what we should, there we go. Cool. So I think we should be able to now, if we hit compile, we'll see our code base is like, hey, this has not got a parameter in, right? Oh no, this is the btrace one. So we'll say, but get string could. Wait, we'll do it in, isn't it? Ignore top count. Excellent, excellent. So we'll take that with us. Pass that into there. So when you do a get string, you do the same thing as well. Nothing called count here. Good point. Same for the other one as well. The Mac one. Same thing again. Sweet, so now we're inside the core abort function that we've got, and now we're passing this new argument. So how many stack traces do we want to ignore? Hey there, what's up? Of course, you can ask a question. Ask away, my friend. So remember, the whole reason why we got into this part of editing this nice B stack trace thing is because it just didn't quite do what we wanted, right? Our test function is one that aborted and failed, but we've got all this noise in here, and it's just gets in the way of understanding what crashed, what's the problem. So now we have this integer that we pass in to say, hey, ignore the top 3 and just give us the rest of the stack trace, right? So that's what we're trying out now. So we're going to put 3 in here. Wait, do we want to put 3? So technically we just want to ignore core abort. Wait, do we want to ignore core abort? You know, we'll pass 2. Pass 2 again. Yeah, I think we'll do that. So yeah, it's just how the implementation works. So it should be fine. So we compile that, go to run. Oh no, it took them off the wrong end. No. Right. So we've got to adjust it the other way around. Got to advance the pointer and take away from the other side as well. Fine. Should I store audio data uncompressed or lossless? Does it matter? I've never programmed audio. So this is something I'll be learning in this project as well. But yeah, I have no idea. Damn it. Yes, I half did it, right? I took away the count, but I didn't shift the view, you know? So I need to like advance it. So don't worry. Let's hop back into the file. So what we need to do is find this ignore from top and just finish it off. So simply all we need to do is a thing called ret here, right? So the best thing to do would be to like say, hey, if that is greater than that, make it that. Okay. And then we can simply say, then we don't need this thing at all. We can just do this like so. And then we can finish by indexing the return, which is the base pointer to the array of stack trace entries. And then just return that on the Windows one. Nice. And the next one would be, so this is the Apple one. So this one is the same thing. So you do it after ret stack trace size, and you'll do that like so. Then what you need to do is then take it away, and then you need to advance it, right? Like that. So we're just going to take this implementation here, and I think it's the same thing for the Linuxes as well. Voila. So give that a go. Compiles fine. Invalid pointer. Passed into free. That's not good. Why is that not good? So we need to do like a mem move. In this case, we need to do a mem move to move the memory, because it's an overlapping copy, right? Is that our best option? You can either allocate another thing, copy it to it, rather than free it. But yeah, mem move is okay. So mem move is one of those things where, so basically mem move is like mem copy, but it allows for overlapping overlapping addresses. Yeah, overlapping address ranges. So the destination is ret0. So we're essentially shifting left. And we want to copy from this to B. So you want to copy the remaining number of elements. So we've already adjusted it, I think. So we should be able to do that times size of B stack trace. Let's try that out. Maybe not. What is this one saying? So he's in an overlapping copy. We're on the Linux one, great. Oh, what's this? Ah. Yeah, just make your own format. Yeah. Well, I'm not sure if that's a good idea. I've never touched audio stuff, so yeah. So yeah, basically I copy way too much memory. I was thinking it's an array of elements of this size, but it's not. So you just allocate one of these guys and then you use the trace thing. Excellent. Right. So basically you're copying. That was horrendously bad. I was not. So this ret thing is this structure. Oh my days. Right. Trace. Oh, so bad, man. I was not reading the code. Right, let's try that out. Give it a build, give it a run. Segful. Oh, because it. Right. What's the size? Void pointer. Bam. Would you look at that? So now we've got rid of this garbage here, right? B stack trace get. We've got abort. You know, do I want that there still? Abort's fine, right? It's definitely two less things. Yeah, I guess it could be helpful. Right. So that's a good improvement. We just want to make sure the other operating system ones are fine. So we've got to go to the Mac side of things. It's basically, well, no, it is the same as the Linux one. So we'll just copy that over there. Cool. Then for the Windows side of things, what we didn't do. Oh. Yeah, here it is. Good. So we obviously set the last one to 0, but we need to shift them off. So it's the same thing again with this mem move. So what is cur or for current, right? what is this thing? See, I thought I shifted it here. Maybe that's fine, because that's the return. But let's just double check this, right? Because it is going to free it, isn't it? It's going to free. So it's the stack trace entry, which is these two things here, okay? So we just want to mem move that and then just return ret, right? So we're just going to sort that one out. So let's just return ret here. Then we'll do that super lovely mem move. Mem move, destination is ret. Let's just do at ret0, just to make it a little bit more explicit. And then we'll say at ret ignore top count. And then we do the number that we got, which is count. Well, is it count? It's going to count take. Ignore top count, isn't it? Yep, we sorted that one out, so it went underflow. Then we're timesing this by the size of that entry. Okay, so it's b stack trace. Wait, I lost it now. B stack trace entry, this guy. Right about there, you see. So I don't know if that works because I'm not running on Windows, but it ought to work, right? So yeah, we'll see about that one run on Windows. So that's cool. So we've now got an abort here. Let's just show the assertion as well. So with asserts and aborts, you can so the assert. You can have some code in here. So I can say like true equal false, right? And then I can say oops as a message, and then I can put format arguments here because we pass these variable arguments into essentially fprintf, and this will do all the formatting, which is super nice. So let's just put some integer in here, like 1337, and then if we were to run this, what you'll see is we get the assertion failed. Our actual code that is in the assertion gets printed out here, and then we've got this oops message, and that 1337 is included all in that message. So you can have essentially variables print out in here as well, which is nice. And we've got a stack trace, and it's shown this assertion failed here right on that test function. And yeah, so this is super handy and is basically a necessity to every project. Right, so where was we actually after this kind of sub-tangent? So we got these assertions in because we were doing the operating system side of things to open up a window, and we want to make sure that we simply don't open two windows or more, because we haven't got we're not thinking about that problem yet. Yeah, so we kind of made a bit of a mess here. We've got too many files open, so let's just close everything that we don't need anymore. So that's a nice modification to B stack trace we just made. So we're going to go back to doing open window. So how does one open up a window in the Linuxes? So you have Wayland, you have X11. Wayland is this new thing. It doesn't quite work on NVIDIA hardware, I think. It's not default on every Linux distro. So until I can install a Linux distro and get Wayland on basically all of them, there's just literally no point in switching over to this thing. Although the screen tearing in X11 is really bad, and if you watch some videos sometimes, it's just horrendous. But and there's probably no good solution for HDR either, and just probably quite a few other things. Like as much as X11 has its problems, it is kind of stable and it works across a lot of hardware. So we're just going to be using this for now. In the future, if Wayland gets better, maybe we'll move over to Wayland. But yeah. How's testing having a game dev environment? It depends what sort of testing you want to do. Basically, you either use printf and you either print stuff out to the terminal, take a look at it, or you hop into the debugger, run your code, step through it one by one, print out the values, take a look, set breakpoints, see what values look like. So that's debugging. But in game dev, you don't typically want to have too many. Like your test code is typically live demos, right? And if the live demos break, and there's that, and typically you want if you have a big enough like studio or a big enough of a or something like that is an essential problem, you would automate that. So if you have like a puzzle game, you would have you would have something that solves your puzzles and tests solving them in many different ways, and you automate it. So it's really specific to your problem that you're trying to solve. But yeah, there's testing and there's debugging in game dev. Yeah, testing and debug it's the same as it is in web dev. Like you do it to solve your specific problem, isn't it? So that's basically it. Yeah, it's a big shame that you can't do it with NVIDIA. It's yeah. One day we can move on to Wayland. I remember like 10 years ago when they were saying it's coming soon. Yeah. But anyway. Oh, is it in the integrated GPUs? Yeah, I don't know if I've experienced the screen tone on my AMD GPU, but yeah, definitely on the Intel one. Yeah, I don't know about this AMD one I'm on. I've not tried it too hard. But yeah, it was so bad. The screen tone is so bad. I was like, oh my days. I remember watching a video and it'll scroll the camera and you see someone's forehead like split. And it's just so weird. Yeah. Yeah, it's another thing, you can hire people who like human beings, so real human beings, you can hire those people too. It just entirely depends on the problem you've got, because sometimes it's just not easy to automate. So what was really great about the HCC, which is my C compiler, which we're going to get plugged in very soon. One thing that was really great about this project is that we had a couple of samples, so you can literally just like boot up and gets a window open and does some graphics, right? Using this C compiler for shaders. So that's cool. So I want to just go in there basically, and as we saw earlier, it's got a very simple interface for those things, and it's a good starting point. Let's just go there, right? So DM for display manager X11. So we need to include this thing called xlib. Oh, a thing to heavily underline here. X11 is one of the most terrible APIs that you'll probably ever see. Well, actually, no, there's worse code, but it is quite bad in terms of modern standards. So just be wary of that. Things don't necessarily look like you have to understand how X11 works under the hood a lot of the time, and it does it really alien sometimes. So yeah, just be very wary of that one. Problem with XCB is that it doesn't have good utility libraries alongside it. Like I tried to do the XKB stuff to do key translations between different keyboard layouts, and it just didn't want to do it. I couldn't do the XIM stuff, so I couldn't translate key strokes into UTF-8 without doing it in my own code. So it doesn't provide any good benefits, basically. It might be a nicer API though, but functionally it doesn't. It's not good enough. Like, yeah, like it can do the basics probably, but it's another thing. If I want to include standard I/O everywhere for printf, probably not a good idea. But anyway, you can always clean up later. Yeah, maybe I have to include them. Right. So what do we need? What do we need to do? So. Yeah, you know what? I think we might want that internal internal header file because we are going to be putting a global in. See, I don't know how much abstraction I want. Do I want to have like essentially a backend? Do I want to have some shared code that sits on top of the backends for these operating system things, or do I want? No, I think that's just too much. Yeah, I think that's just too much. Right, so let's make an OS Linux internal header because I want to define pragma once. I want to define a OS Linux structure. So we're going to use a global variable here just to store all the context and everything in. Nothing's really going to include this except for this. Yeah, nothing is going to include this except for this oslinux.c file. So the idea here is we're going to have so X11 has these really it uses the most general names for some things and it's so annoying. So like the word display is used. So no one, if they use X11, can use display if they include the header file. So, but also, it's very hard to tell sometimes what is an X11 thing and what is your code. So what I'm going to do is I'm going to prefix all the things that X11 does not prefix with X11. Right. Sorry, it's the other way around, isn't it? So this way it makes it easier to read like what is X11 and what is not X11 stuff. Right. Why is the field incomplete? I don't know what it's talking about. Let's have a look. You don't have to go strut display. Oh, it's got to be a pointer. Right, it's got to be a pointer, that's why. Yes. Okay. Okay. Yes, I need one of those. So basically, a display is a connection to the X11 server. So X11 runs in a separate process, and the way to communicate with it is like a server where you send it and then receive stuff from it. Typically, you use higher level functions to achieve stuff, and then you need to flush or sync with X11, and it will do the whole send and receive behind the scenes for you. But yeah, so basically you want to start off with opening a display connection. So we might call this, it's a terrible name. I'm gonna call it connection. What do we have in the window before? Window, I called it handle, didn't I? Okay. Yes, this OS Linux thing, we're just gonna say static. Well, not. So with all my globals, we're probably just going to put a G prefix there, so it's a little bit apparent it is a global. It's kind of a nice thing you can do. And we are going to have functions that we declare in here, so we might say OS Linux X11 handler. We are going to drop that in there like so. And then we do obviously want to declare this here. Yeah, I think I want to put the internal stuff at the bottom. That's where I want to roll. Public stuff at the top, internal stuff at the bottom. When you play the worst part, is the worst part essentially the shell part. I've not played with WinAPI. I know about Win32, but what's WinAPI? First Google of the stream. Oh, the shell part of it. Right, I've never used this. I have no idea. Yeah, I don't know. But yeah, maybe it is quite old or something. I can imagine that. I'm out here, can't even get started with multi in VS Code. What do you mean? What's up? I am kept paying. What do you mean? You can't get set up with multi-file Raylit? Yeah, if you're struggling with anything C programming, if you join the Discord, you can ask more long-form questions there, and there's more people than me who can reply and help you out. But yeah, if you're struggling with C programming, just post your question in there, and I'm sure you get some help. Would it be better to get keyboard mouse input from the kernel instead of going through the Windows system since the server client? Let's see. So I don't think you can. From what I've tried, you can't actually get hold of the file descriptor for keyboard input and mouse input, but you can for gamepads, I think. For some reason, I think the X11 display manager actually opens that file descriptor and you can't open it anymore, I think, from what I've tried in the past. And another reason why you do want to use the X11 way is because you get their you get all the extra stuff on top, basically. Like they have some utility functions in there which basically do the heavy lifting for you for a few things. And it plugs in with like, hey, I've typed on the keyboard and my window is focused, or this window over here is focused. But although you could probably do that for yourself by just checking if your window is focused, and then all keyboard input from this point goes through there. But yeah, there's I think there's a limitation basically. Right, so we've got this GOS Linux side of things. Connection is going to be equal to open display. So this opens the display connection. You can pass in some environment variable because you can do like some across the net. You can basically do remote X11 stuff with like another computer. So you can do that. But yeah, we're not going to do that. So we're going to do core assert. That's what we're going to call that. Could not open X11 display connection. And then we're just going to get this delete message atom. So what is this thing? Why are we doing it now? Because if you're going to close your window, you have to, for some reason... Is it if you close your window? Yeah, so basically an atom is like a deduplicated string, and you deduplicate your string with the X11 system. You get back an atom, and this atom is like a string identifier, and it's unique. Like every string that is the same gets the same atom, right? And again, this is going back to just because it's a crazy old API. You need this atom when you get an event to say when the close button is being clicked or something like this. So we'll see that in a bit. So we've got this X11 handler as well, because for some reason, sometimes when you get a bad error message, sometimes it doesn't show up. So we're just gonna do an abort here, core abort, and we'll get the buffer and print that out there like so. That'd be good. So we get stack trace as well. Be nice. Since there's a callback. Cool. Right. So we actually need to make sure we initialize these things. So let's hop back into the main C file. And we're just going to go ahead and initialize our operating system context. We're going to get rid of this test thing now. And then we're going to call this operating system. Let's get a window ID. We're going to do 800 by 600. And then we're going to go to sleep for about 5 seconds. And then, so that's going to be our main function, right? Open up a window, sleep for 5 seconds, and then close program. And now we just need to implement this OS window open for Linux. So here is a very simple example. It is going to change, like there's a lot more stuff you can do, and we will be extending it in the future. But for now, we just want to get graphics on the screen today. So we're just going to do the most simple thing. So we're going to have this thing called like an OS Linux window. Wait a minute. An OS window. And this is going to be so we need to have the, okay, this is another one. X11 takes the name window. It literally has the name window, so it's really annoying. So again, we're going to do a thing called X11 window, just to make it clear that it is actually from the X11 code. So silly, so dumb. So we'll have the X11 window here. See, I'm not sure whether I should put more abstraction to this. I have more, and have it called into some specific functions for the Nah, let's just leave it. So you know, we don't support multiple windows yet for now. So the most basic thing we can do is just stick it in this global thing. In the future, we're going to have like an object pool or something like this, where we just say, hey, the maximum number of windows we need is 16, and then we just sort of like recycle the array slots. but we'll build that in the future. Don't need it now. So we just need to edit this code around. So we just want to say GOS Linux dot oh my days. Bono Montana, welcome sir. Welcome sir, how you doing? Good to see you. Will all episodes be on YouTube? Yes, they will. So if you miss anything, you'll be able to go onto the VOD. There's a VOD channel. And I also have a YouTube channel where we'll be posting some shorts. Not shorts, not YouTube shorts. I'm not that much of a... I'm not that into my YouTube. Posting small devlogs. Trim the beard? Yeah, man. Yeah, it was big. But also, if you are a Twitch subscriber like Benny Montana is, you'll be able to join the Discord and check out this channel, and you'll be able to get access to the code base that we're writing and see all the commits and everything, and download it, tinker with it, and yeah. No worries, no worries. Hey, the Toggle, good to see you. Good to see you. I've been listening to your podcast. It's been good. Been enjoying it. Why did I quit i3? Because I wasn't using i3. I was using Spectre WM, and the tiling window manager was good, and I did like the experience. But the problem is it did have bugs, and I got a new computer, which is really cool, and I just fancied something different. And I kind of really like KDE anyway, although the tiling window manager is like, the workflow is nice, and I do really like the keyboard, using full-on keyboard a lot of the time. But also it's not that much of a pain to not use it. Yeah, I think the bugs were really kind of annoying. Yeah, it does come with a built-in tiling thing now, doesn't it, KD? I've just not been bothered to set it up, I have seen that. I think you could do like, I'm not going to bother trying. Yeah, and the computer's awesome. I've had it for like three or 4 months now. But yeah, it's cool. It's awesome. It can now do graphicsy thingies, which is good. There's too many D's in here, GOS Linux connection. Right, so I got to explain what the crap is going on here with a lot of this code. Let me just give a bit of a... Let me just change this for a minute. Then I'll get you all updated. Right. So let's go from the top. So again, we didn't do multiple windows, we just crash if we do multiple windows. Our ID is just going to be 1 because 0 is null. Right, 0 is an invalid window ID. I forgot what a screen is exactly, but I think it's like... It's essentially like another monitor, maybe. You pick the monitor that you're on. I'm pretty sure it's that. I'm pretty sure in X11 terms. So you can use this screen thing, get the default screen, and get the root window, and that's your parent window. So this is the parent window. We're using this create simple window, passing the display or the connection with the X11 server, display connection as it's called. We pass in the width and the height, 0, 0, width, height. So this is an X and Y. It's not always respected by because the X11 protocol is implemented by different desktop environments on Linux. Not everything respects what it's passed data, and it doesn't always respect all data. So that includes X, Y screen positions, width and height. It just doesn't. It could do whatever it wants. But typically they don't really like these anyway, so we're just not going to pass them in. You know, we could do no. Passing the width and height. I forgot what this one does. Black pixel, white pixel. I have no idea where I have to pass, but you do. So there's this X create simple window. In future, we'll probably just use X create window because there's another function that does that. But this will make your window, it will open it up. But just calling this doesn't open up the window. Because it's a server and you're a client, you need to actually flush what you've done. So essentially it's queued up a command which is going to go to the X server next time something is flushed. So we'll call flush to flush it. But before that, we want to do some things. We want to say, hey, this window would like to receive some events. So we pass in the event masks. Again, this is really terrible because I cannot tell easily. I can't find easily like the event masks. Like I think in the headers, it's a bit of a pain to find them. It'd be nice if they had a prefix so I could search for them, but they've just got a suffix of mask. Super helpful. So you see, we're going to get some key presses. We'll get some structure notify, which means resizes, and exposure, which means I think showing the window, minimize and maximize. I think something like that. I forgot. And then map window. That means I'm gonna. So by default, the window is not shown. So map window will show the window, and then we're going to set window manager protocols, and you take this address of this delete message atom, which I forgot what this does exactly, but we'll look in when we process some events. But I think when you press the X button on the screen, it's going to now send an event to say you've pressed the close button. Now it's up to you to see how you want to handle it. So I think if you don't define this, it will just close the window. But we want to have our own shutdown code. So we have got to do this silly thing, which will then give us a certain event. And then we check against the event and the atom it gives us. And then that's a quit event. And then we can quit. And then we flush it all. And then now X11 within so many milliseconds or whatever will respond and put it up on the screen. So that's how you open up a window. So let's try this thing out. What stuff did you miss, Toggle? We've basically set up the file structure. We'll get a bit of a... So game without an engine, we've got a build directory, we've got scripts directory, which has our simple build scripts, which just invokes the client compiler. We've got our third-party folder with a third-party library called bstacktrace, which is 400 lines of code, which gives us a beautiful stack trace, which we've got up and running. So as you see here, we've got some stack traces if an assertion fails. Got lovely assertion messages, all ready from the get-go. We also have a source directory with some core files. So core is going to have like our custom memory allocators, our collections, memory utilities, time utilities, stuff like this. A main C file for where the main function goes. And this is the thing that we compile at the moment, and everything else gets included into it. And then we have our operating system abstraction, where we simply abstract across the operating system, and we have 3 functions right now, which is OS initialize, OS window open, and OS process events. So we're just going to get a window open now, and then, yeah. Did I write my own stack tracer? No, so I've written one in the past, but I couldn't quite find the code when I did it for my C compiler, my C shader compiler. So I searched the internet for a single header. Turns out there's one called b_stacktrace. If you search it up, you'll find it. Like that name there. And it's 400 lines of code, works on Windows, Linux, and Mac. Like I'd already written that code somewhere before, and I looked at it and it looked pretty good. We literally had to add a feature to it today. So would it ignore the 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 first so many stack traces when it printed it out? But other than that, it's a really good library and it works cross platforms, so I highly recommend it. Yeah, exactly. Third party. Yeah, that's right. Ah, Downsy, how's it going? Good to see you. Good to see you. Oi, oi, oi. Yeah, yeah. Does one have his wrist braces and almond milk? No, I'm wrist brace free, my friend. My wrists are all healthy. And also, I don't really drink almond milk anymore. I used to drink almond milk when I went vegetarian years ago, but not anymore. I don't really drink milk anyway, either. You know. What the funny thing is as well, it's not really made of almonds because you know how expensive almonds are. Almonds are like so much more expensive than what you buy in that milk carton. It's like flavored with almonds. I bet you these are one or two almonds for the whole thing. You know. Oh yeah, awesome. Yeah, connect up to that Discord. Beautiful. Hmm. So now your name will be, I think it's blue or purple. I forget. I forget these things. And now you should be able to see the link for the GitLabs. It takes loads of time to milk the free range almonds. Exactly, like how do you milk an almond? Yeah, so like effectively almond milk is just water with like B12 added to it and B6, and then they like do something with almonds to the water. Like they like probably blend them up or so. I have no idea. But it's definitely not, hey, I want to take 100 grams of almonds and milk these things. Like it'd be way too expensive. But yeah, how's it going, Downsy? Good to see you. Good to see you. Yeah, so let's press the F5s, which means build. Redefinition of OS window. What is going on here? Where's the other definition? Oh. Right, let's sort this one out. Press the F5s again. What's this? Undefined reference to X11. So, why does one get this problem in C? Well, the reason why you get this problem is because X11 is a dynamic library, which means it's like a .so file on Linux. On Windows, it'd be a .dll. Not sure what it is on other platforms, but it's some different file extension. So it means there's precompiled code in a file that exists on your system, and you have to link against it. You can sometimes statically link, which means bring code from a .a file into your executable, but I don't think it's a good idea to statically link against X11. So we're just going to dynamically link against it. So you basically just need to tell Clang, our C compiler, to we just need to tell Clang our C compiler that we want to link to it to X11, right? So we can see we're already doing it here. If I were to say LDD, which means show me the linked libraries. Okay, I can't show it now. We'll see in a second. So we're linking against maths because the maths library is actually the C standard maths library is actually a separate DLL. Sorry, separate library for some reason, and so is DL, which allows you to dynamically link to libraries at runtime by calling DL open, which is something we will be doing in a minute when we start with the Vulkan code. But we're going to do with X11. So there's a file in some lib directory called libx11 .so. So by saying -lx11, it's saying search for a file that is got this name. That's basically what it's doing. And if it's not in your search paths, you need to, like -I, we're saying, hey, include this include path in third party. We need to do a -L, and then you provide a path, because you can make your own libraries as well. And and it'll follow the same thing. You need to call it lib something, and then So now we recompile, we'll see that it works. Awesome. If we run LDD, this prints out all the libraries that we link against. So we actually link days. Okay, so I'm actually using XCB under the hood because X11 uses XCB under the hood. Right. Layers of abstraction. Here we go. So So typically, like, you want to avoid linking to too many system libraries. Like if you use like Arch Linux, or Ubuntu, you typically install libraries to your system. And this doesn't really make a very portable executable. So if you were to use any libraries that are not basically provided by like the core, like are the foundation of the operating system, or are not provided by the graphics driver, for instance, you typically don't want to link against these things. Otherwise, if you take it to a distro that doesn't have it on the system, it won't be able to run. So you're better off either shipping it with your executable, or compiling it in statically. So that's why we have a third-party folder as well. What happened to the build system in C? Just plain bash now. Yeah, we will move to doing a custom build system, but for now we don't have thousands of lines of code, so it's not really that beneficial. But as soon as it starts getting noticeable, we'll spend a stream doing that. The milk and almond discussion. Awesome, we've got answers. This is great. They keep an almond close to the water. Great. You soak almonds and then you use the water to make almond milk. It's not made by blending almonds or anything like that. Okay, right, so you just soak the almonds then. That's good. Good to know. Okay. I wonder, okay. Then are these almonds like resold? Because I haven't seen those almonds. Yeah, so there's the mess and build system. There's pre-make and C-make. I've tried messing out. I've tried C-make out. I've tried all these things. They're just extra complicated for no reason. Like, you can basically get Clang to give you the dependencies for all your files, and you can build a custom build system like really easily, and it doesn't. You have to learn some like they're so complicated for no reason. Like, it's literally just calling the Clang thing to build separate C files into these .o files when they have changed. So you just need to do some file timestamp checks, and then it just links them all together at the end. Like, it really isn't a hard problem, and the way you have to express that in the CMake thing, it's just weird. Like, yeah, so we'll just build something specific for our project, and it will just be fine. Yeah, or include everything, keep it simple. Yeah, there's Ninja too. Right, Ninja as well. Ninja basically does the timestamp. Ninja basically uses Clang and gets it to give it the dependency list, and then it will only compile the ones that you need, and will create multiple processes that run at the same time to do it in a multi-threaded way. Yeah. So Ninja is an option, but again, it's not too difficult to write that, I don't think. Like, it just doesn't. It's a very simple problem to do, to solve. So, cool. So we compiled it. Now let's run it. So here's a window. It's going to be here for 5 seconds and it's going to close. So that's really cool. That's super nice. So now I've got a window. How do we... So 800 by 600, did it even listen to us? That was pretty square to me. Parent XY width height. XY width height. Border width 1. Right. Okay, it's border color, background color, right, white. Got it. Sure. Yeah, early access. Yeah, ship it. Yours only for $5.99. Yeah. Simple white window. So typically what you'd do is you'd have like a game loop where it's just an infinite loop, and we close it when we want to close it. And typically you'll start off by just processing the events. Now, so what we want to be able to do is essentially get the next event. Now, what did the process events do in this? Is X pending, gets the event, translates it. Cool. So what we want to do is essentially have events next. I think I want to call it, or maybe iterate next, right? To say it iterates it. So we maybe have an events push, so you can push a custom event as well onto this event stack. But yeah, so we're just gonna basically want to implement one of these guys. So let's go and grab that code from the sample project that we've got before, and we're just gonna explain it all. So this function returns true so long as it gives you an event back out via this out pointer. So we're going to call it eout for event out. Maybe just call it event eout. Okay. So effectively, we just want to say GOS Linux dot connection. Okay, so we need to do unused parent. Let's just correct all this quickly, and then we'll go over exactly what it does. Explain it all. DM window width, window height. Right. Oh, there's a lot of stuff in here. DM. I know Perry's looking at me right now. Just use /s. Yeah, no, yeah. Just do find and replace. Way better. 350. Yeah. 350. Yeah, black pixel is probably a good idea, innit? Yeah, let's do black pixel. Border black, background black. Much better. Good idea. And this is the whole reason why we write the custom engine, right? Okay. So what have we got here? So if you remember in our interface, we have this event structure. We're essentially got pointed to this event structure, and we set the type. This type will either be key pressed, key released, resized, or closed, or it'll be unknown. And unknown just means like maybe something has been uninitialized or whatever. Yeah, I'm not sure what we want to do around that side of things. But anyway, we have an unknown. So if the type is key pressed or key released, then the field that's available to us in this union is key. Now, key is a char. That's not good. We also need to change this for a game. But remember, this came from a simple sample application, and what was good enough for that application was an ASCII key character to just say, oh, press the A key or the B key. And that was fine. But for this is an actual game, and we want proper key codes and everything. So we're gonna leave this in for now, but this is gonna change, right? So I'll put a to do proper key code enumeration. So what is this? Window width and window height. So if you resize the window, you'll get this. This would be for this one. So we'll say resize is this guy. And then there's a handle here, probably for the window. So you probably just want to say, right, OS window ID, because you have multiple windows, right? What is the ID of the window that received this event? So that'd be super handy as well. Cool. So we're just going to be poking that memory with the correct values every time we iterate over. So how do we do that? While expanded, doesn't that make the app wait for long? Yeah, so X next event makes it wait. X pending checks. So X pending will, if there's nothing in your queue, it will, if there's nothing in your queue, it's going to ask the X server, is there any new event? If there's no new event, it will return false. But if there is, if you have something in your queue, so it just reads an integer, and the integer will be like, oh, I've got 3 left. And then if it's got 3 left, it will return 3. And then when you call next event, it will take that number, that 3 variable, take 1 away and give you the latest event. So it only really contacts the X server once, and it doesn't block. It's non-blocking. Whereas X next event is blocking, I think. Let me just double check that. X pending. Oh my days, sorry for the blinding white screen. Returns the number of events that's being received from the X server but have not been removed. X pending is identical to events queued with queued after flush specified. So if the mode is after flush, returns the number of events if it's a non-zero. If there are no events, flushes the output buffer and attempts to read more events from the connection, returns the number of events read. So it doesn't block, right? Yeah, the next event is the blocking one. Yeah. So yeah, so we just use while X pending, and we're only going to return when we have an event that we noticed, right? So what would actually be a good thing is if we were to print here and say, hey, there's an unhandled X11 event, new line, and we'll say xe.type. So essentially we're just translating this x11 event structure into our own event structure. It's a very kind of similar thing, this x event. So we say x pending, we do a next event, which is like this function, but gives us one of these, and then we translate it into our thing. So this is just the nature of abstraction, right? It's typically just translating from one similar thing to another similar thing. So if there's a key press, it will do a key press event. Remember, we're not sticking to this, but this translates it into a char character, like an ASCII key character. We're not sticking with it, but it's just a temporary thing. We've got key release, same thing. We have this thing called client message. And this is the thing I was talking about earlier, where if we do this sort of set window manager protocols thing with this delete message atom, which is a deduplicated string, right? If the client message that we got is this atom of so bad. GOS. It's such a terrible design. But anyway. Then the user has requested to close the window. So we're going to then send an event back to say, hey, the window's been closed. What do you want to do? And then the final one that we have decided to look at. See, again, these things are not prefixed of anything, so they're so annoying to try and find what these things are, right? You have to Google all around or look through some headers, and it's just basically sample code helps you write X11 code really easy. There's no good. The documentation is like quite difficult. So Xconfigure does a few things. It does resizing and positioning. So because it does resizing and positioning, so it's like hey, the whole box has been changed that's on the screen in some way. So we're just going to say, hey, if our known width has changed in some way, then it's been resized. But obviously, if we change if there's a window position one, we might have to refactor how this whole thing works. But for now, this just works fine. We might have to have some Q or something like this. But yeah, for now, this works fine. We can refactor it later because this is all we need right now. Let's go ahead and go into the operating system Linux internal, pop in here and record a width and a height. Default values will be 0. And remember, we just have one window for now. Goes in the global variable, and voila. Different signs apparently. Cool, thank you. We'll probably cast it to an EUINT. Nice. Right, so this will be super handy. So now we can say while next event, we get our operating system event. Call it E, I guess, or event. Address of event, and then we do our switch on event.type, and now we can handle all these different events. So we just want to get these guys. I should make that a 2 key press to highlight all that stuff. Yeah, what am I doing? So I'm doing like 5 S's, super lovely macro. So we probably just want to say, like, you've pressed this char key, right? Again, we're going to change this to be an actual key code in the future, but for now, this will do. Then we've released. If we resize the window, window resized. See, yeah. Yeah, sometimes I like to make a function which just debugs this stuff, so you can just debug print the event. But for now, we'll just handwrite it and copy and paste it to that. Event window width and event window height. And then if the window closed, we're just going to exit. And if you don't call exit, it's not going to do anything because we've said we're going to handle this ourselves. And if you have multiple windows, you don't want to close unless you're the last window to close. And when you close, you want to shut down the system, maybe save some files, do some stuff. Right, so there's more things that you want to do in the future, but for now, this should be enough. Compile it, compiles it all, we're good. There's a poll function, you think? Yeah, that's what the xpending does. It polls for the events, right? So during the resize action, the event loop will keep looping. No, it won't keep looping. It won't keep looping. It will just resize, do a render. Well, yeah, it just processes the events. So you will. Oh, yeah, I'm not sure what you mean. Yeah, so we'll get the next event. It will if it is a resize event, it will return true, and this event has already been taken. You will handle that, and then you'll just, when you've run out of events, you'll render the frame, and you're not going to resize it and stop it. You're not going to keep resizing it and stop it from rendering it. Like pump it with enough events to stop it from doing a render. But yeah, sometimes, yeah, I'm not sure really the best way to handle a resize event anyway. Like, sometimes it's better just to maybe resize and let the game do nothing. Like, yeah, only do the resize when the person has stopped resizing the window or something like this. But yeah, we'll see how that goes. Is an event key global per application basis? Per display connection, I think. Yeah, per connection. Yeah. Is the code available on GitHub? No, the code's not on GitHub. We, although if you sub via Twitch or support via Ko-Fi, you'll be able to get access to the code. If you take a look on the Discord, there's a channel, and it will go over the different options. But yeah, if you have Amazon Prime, I think you can still sub with Prime, and you can get free access to it. So there's that method. Oh my days, Toggle, such a generous man. Thank you, Toggle. I remember detecting key repeats was tricky. No, it's not too bad. Yeah, you have to use the XKB thing. I've got a file. I've got an old abstraction that I've done. You basically can disable key repeat. No, yeah, you can disable key up events, and you can detect whether it is a key repeat quite easily. Yeah, I've just got to dig the code out for that. But yeah, well, that's a future thing. At least when I did it on X11, it's not so bad. Right, so we compiled that, give it a run. Black screen. we've got a window resized to 800 by 600. Apparently it's 800 by 600. I can't. But anyway, we can't see any mouse move in there because we're not handling those events. But if we give it a resize, you'll see that it's doing some resizing. Also saying it's unhandled. There's some unhandled events in there. We do some key presses. Pressing on the keyboard, right? There's no releases for some reason. I don't know why there's no key release. Oh. Only when you hold it down does it tell you there's a release, right? Okay. Interesting. But yeah, this is good enough for now. If I press the enter key, it doesn't like it. But if I close it, closes the window. So there we go. We've got ourselves a game loop processing some minimal events. So now it's time to probably do some graphics now, don't you think? Like, should we do some Vulkan and get compute shader going and start that thing? So what I want to do is I want to commit this and put it up on the GitLab so people who do have access to that can download it and take a look, tinker with it on their local machine. It has to be on. We don't have it on Windows right now. We will do that in a future stream. Possibly next stream if everything goes well. Today we'll be able to go onto Windows and get that all set up. But yeah, so we've got a couple of files starting out, which is good. So if we do a git status, we've added. Well, no, we're on this build directory, right? So we're gonna add a git ignore. I want to ignore the build directory. What else? What else don't we want in here? I'm gonna put the compile flags in there. I'm gonna put this clangd thing in here just in case people are using that on their system. We've got scripts directory which has the build script in it. Just a simple build script. Source directory, third party folder, and the source directory has core for core utilities like custom memory stuff and collections, which we don't have yet, but it's got some other utilities like assertions in there. Our main file got some operating system abstraction as well, where we have an operating system interface, and we essentially implement functions like opening a window on Linux and opening a window on Windows and processing an operating system event on those platforms. So that's what we have so far. So we're going to say like git commit. Yep. So we essentially have like essentially opening or like open a window on Linux and have stack traces, right? Stack trace, asserts, and aborts, which is super nice. So let's push that up to that's not good. Yeah, it's 2 minutes. I gotta go and revoke my damn key. It was too smart. Settings. Why can't we have nice things? I just pushed it's revoked now, so I can't do anything. But yeah, it's up there now. But yeah, I had a key, and then it's like, hey, I'm just gonna blurt this thing out. Thank you. But yeah, anyway, so that would have given like everyone like read write access to the repo, which would have been not good. But anyway. So that's revoked now. But anyway, so if people with access to the repo, it'll still work for you, because there's a different key for everyone else. But yeah. Anyway, I'll sort that out later. Cool. So what's the next thing we'll be doing? So we're going to be working on creating a Vulkan instance and hopefully getting a compute shader running and setting some pixels on the screen. Quick 50 lines of Vulkan to pop a pixel on the screen. Yeah, it won't be that too many. There's no triangle. It'll be a rectangle. It'll be like this one. We're not doing triangles. Triangles are banned. Yeah, so it's actually gonna be a lot less because we're only using compute, so it'll be very simple. And yeah, so it'll be like this. We'll try and get something like that working. Yeah, so we're using this single header library called bstack trace. You can give it a Google. Yeah, bstack trace by this guy. We had to change it a bit so we can remove the things at the top, but you should just include it. Like I've written one of these before, but it's yeah, it's only 400 lines, works across operating systems. It is good. I know the crap from the X11 release when the holding button used call X. Yeah, something like that, yeah. Why don't you use an SSH key? Because GitLab sucks. I used an SSH key. It worked for pull, but it didn't work for push. And it kept telling me to re-enter the same password again. And I've set it up right. I can do a test SSH thing with it, and it just all looks fine. And I tried Googling for the problem, and I can't find a solution for it. So yeah, it's just really bad. Like I've tried everything I can think of. So I just did the quick thing of just using a project access token. It just worked. Yeah, I've done everything. I've got the remote. Yeah, I've done it with SSH. Yeah, I did it all. Yeah, it's weird. Like I can show you. I can literally show you. Like, so here's my GitLab. I've got my SSH key set up there. Like, it's on my account basically. There's a public key thing. Anyway, it is there. So if I do a git remote add origin, not this one, right? You want to do SSH. You know, maybe works today, and that would be awesome if it does. I'd be happy if that is the case. I think you have to do a colon in here or something like that. But you do a .git. Git at, and then you do colon. Clone SSH. Yeah, colon. Yeah, that's it. So I've done it with the explicit SSH // as well, just in case. Obviously I could copy that, but right. All right, I need to say set URL. Yeah, there you go. So we'll try this. If I do a pull, just to show you. What? This is not the one I had. Or just a git. Right. Yeah, no. This is not the error I had earlier. Right. Use SSH or the git. Okay. Or just git at. Right. Okay, let's try that one. Right. Yeah, so this is my RSA thing, right? I type in the super secret password. It will say I'm up to date. But if I try to do a push, right, I'm going to type it in. It takes a while. Then it asks me again. But if I just type something simple in, it comes back right away. So it's like it tries and then it fails and it comes back. So I don't know. I don't know what this is. If it's some verbose thing, I've tried to do -v, it doesn't work. But if anyone knows how to fix that, that would be awesome. But yeah, I've literally got the SSH token in the GitLabs, and it was my public key, right? Because it works with the pull, but not with the push. Yeah, it's generated with a password. Yeah. Update Git. I'm using latest Git. I'm on Manjaro. I don't know what. But yeah, I've got like my public key up here. So yeah, it doesn't. I've tried the verse output. It doesn't show. So you need to enter the password to unlock the key. Yeah, I did enter I entered the password in here, but it works for pull, and when I enter the password, it works. But when I want to do it for a push, it doesn't like it, and it will wait for 2 seconds, then come back with the same question again. Or is it my GitLab password? Yeah, I've done that eval thing. It doesn't work. Yeah, I've done that. But maybe it has to be my GitLab part. No, but it can't be. No, because it's same for this thing, doesn't it? Yeah, SSH1, isn't it? Yeah, I've tried that eval thing. Look, if we're going to bash and I type, yeah, I did this eval thing. Let's try it, right? But I did this, and then I did SSH add to my GitLab RSA thing. Enter the super secret password. Right, so it's added it, right? Right, I'll try SSH git at gitlab.com. Welcome. Connection closed. So it works, right? Now let's try the git push again. Yeah. And it just doesn't work. Like, and see how it took a 2 seconds there, but if I put something fake, like, that doesn't work, it just comes back right away. Don't exit bash. Is that the problem? Right, let's go back into bash. Wait a minute. That one, that one. Then I do a git push. It works. So why? Right. So how can we do that permanently? Okay, well at least we know how to do it. Yeah, so something fishy was going on, that's for sure, isn't it? You have to do it from fish somehow. Awesome, thank you so much, Leviska. Your name is I got a black background and your name is basically kind of grey on my screen. It's like so hard to read your name, but Leviska, thank you so much. And Perry sir. Thank you so much. Vim.pro. Oh, wait a minute. I've got to do the eval. So yeah, this is gonna agent dev null into the dev null void you go. Then SSH add whatever that thing is. FG for that foreground. Oh yeah. And then do that right. So that should work from fish, right, as well. Should we give that a go? So I exit everything. Let's close everything. Get out of here with that one. See if it works. It's asking for a passphrase still. Need relog isn.profile, is it? Right. Well, that ain't gonna happen. Let's see if we can say like, can we like reprocess the, or like fish. So we could source it, I guess. Does that work? No. Oh well. I'll just see if it fixes it next stream. Right. Awesome. Thank you very much for that, guys. Appreciate it. So I could just try source, right? But will that work? It's in fish though, isn't it? Doesn't like it. I'm using yeah. Yeah, it'll be fine when it reboots, probably. Let's give that a go. Let's try it. Huh. I didn't like it. Yeah, that's all right. I'll just see if I can fix it off stream. It's not a big deal. But at least we know I can just log into Bash. I can run that thing. It should be fine. Oh, will it? Yeah, so if I write Bash now, oh, it doesn't do it. Oh, so it's the SSH agent. So is that what it's launching? But doesn't that agent need to be running anyway? I'm confused. It's weird. Oh well. It's login only. Okay. Good to know. Cool. SSH agent is the thing that remembers passwords. If you run it in profile. Yeah, it's just like a daemon, right? But not. You're having every terminal shared. Okay. It's weird. Okay. Well, that's good. I don't have to remember the password in future then. That'd be cool. Right. Yeah, makes sense. It's permanent. Yeah, that's good. Yeah, that makes a lot of sense. Right. Okay, so what's next is we're gonna do some Vulkan code. We're gonna create a Vulkan instance. We're gonna select a GPU. We're gonna set everything up, create some command buffers, record a dispatch a shader that's been compiled with HCC. We're going to bring that into the project. We're going to compile have C shaders in the project. We're going to set up a GPU abstraction, and we're going to get a compute shader running. That's yes, that's what we're going to be starting on. But I just want to take a quick 2-minute break. I'm going to get a nice tea, get some more water probably, and then we'll make a start on that. So yeah, I'll see you all in a couple of minutes. Did my tunes stop? It did. Right. Enjoy the tunes. I'll be back. Hey, welcome back. Oh, you can't hear the music? Yeah, I think the music is a bit quiet. Yeah, you should be able to hear it. Maybe we need to up the decibels. I don't know what's going on with that because I saw it on the thing there. Oh, weird. What flags was a passing SSH agent? I'm not sure. But yeah, it's working now though. There's no need to worry about it. Yeah, we will be doing some form of custom rasterization, but not yet. We're just setting up the foundations of dispatching a compute shader and things like this. But yeah, we will be getting there. We just need to build up the foundations a little bit first, and then we'll be doing some R&D. So we'll probably start with doing some 2D rendering, like doing a bit of rendering a little bit of UI, getting the keyboard hooked up, getting a gamepad hooked up, and then after that, we'll actually get on doing some more 3D rasterization of some kind. Oh, it says I can use eval. Is it on fish shell? Excellent. All right. Yeah, maybe I won't need it because I use Bash as my default shell, but only in console do I use fish. So I think it might be fine when I log out and reboot my system. The dot profile stuff should work. So that'd be super cool. Right. So what are we gonna do now? So we've got a source directory. We've got these operating system files. We've got main file and a core file, but we want to do some GPU stuff, right? So with a GPU, I think we want more abstraction than the operating system stuff. I think we might want to have like, yeah, I think I might start making folders and put these things in folders. Yeah, I think I might start in folders. So we're going to make a directory, make a couple of directories called source OS and source GPU. So that's straight. Welcome. Thank you for the follow. So we're going to move all this operating system stuff, operating system dot h to source OS, and then we'll also move OS underscore star in there as well. Do a git status, what we've got. So we've moved them all into the operating system directory. Nice. And we probably want to do something like that for the, so we want to open up the, so do a nice grep for probably something like OS. You know what? Nah, it's not probably doing that. Is it just the main that does it? Right, main OS/OS Linux. So I have to hop into here. Right, there's too many layers there. Finally found it. So Right, nothing else includes the operating system stuff, does it? Well, the core will eventually do that, but it's not got it in there now. All right, so that's good. So we'll still be able to open a window with that. Should we test it? Compiles just fine. Then we should be able to run. Wait a minute. Yep. So we should be able to run. Here's our window. Right. So now what we want to do is get some graphics. I'm only using Fish Shell as part of console. This terminal emulator. So in this terminal emulator, in the preferences somewhere, wherever that is, I don't know if I can get access to it too easy. But yeah, inside the preferences, where the shell it's using is Fish, whereas the startup scripts and everything uses bash and that. So we don't. The default shell is not Fish, basically. It's just default in my terminal emulator. Some temporary memory and string handling. Yeah, we probably could do with those sorts of things, but we'll add them as we need them. Yeah, especially like temporary memory allocators and that, right? They are very handy, but we've not got. Yeah, like also like a custom allocator that just you use to initialize the application, and you like just allocate a big like a buffer that's large enough to store all the memory you need just to allocate or just to boot the program and set everything up, But yeah, we'll sort that out as time goes. For now, we just want to get some graphics on the screen. Yeah, the extensions and things. Yeah, I think we can kind of avoid that for now. But yeah, that is true. I think you get by with just using standard string utils. Right. So what is the level of abstraction we want to do? So let's touch a couple of files. Let's hop into the source directory. Let's go into the GPU directory. Let's see, maybe. Yeah. So if we touch, we want a GPU.h, we want a GPU internal. Do you want internal? Yeah, internal.h and a GPU.c. So these are the only files we're going to have, which implement everything to do with the GPU API that we want. So this is meant to be a higher level abstraction on top of Vulkan, maybe DirectX, maybe Metal, like whatever like graphics APIs we have, right? And then we'll have some form of like backend API, which there'll be a backend API that the backends implement. And then we probably have backend Vulcan.c. Maybe just have a backend folder, Thank you for the follow. Appreciate it. Welcome. There's too many long names. Is this good? Internal and an internal header as well. Maybe. Yeah. As Anakin Skywalker says, this is where the fun begins. No, not DirectX 11. No, we just do Vulkan. But I meant like in future, if we need to add a DX12, 12 backend, we can do that. But yeah, we're going to just be doing Vulkan. And if we need to add more, we can add more. Just going to abstract it enough for what we need. So I think this is what I want. Yeah, this is what I want. And these are probably all the files I ever need. And everything outside would just include gpu.h, right? So let's go. Let's include gpu.c here just to include this main compilation unit because I'm being lazy about a build system right now. We also include backend Vulkan. Again, we're being lazy about it. Like we should probably if-def this thing. You know, tons of things, right? Could be better, but for now, this will do. We're just trying to get a compute shader running. So what do we want to achieve here? So we're gonna have some form of GPU system that will be initialized. It will probably take some setup arguments and things like this, but yeah, we don't know yet. So there'll be something. So this is the public interface. We're also gonna have some form of backend API that's implemented for each backend. So what things do we need to have to achieve? Like what functions do we want in our main function to talk to the GPU and do things? So we probably need a concept of a resource. So when I say the word resource, I mean image, buffer, or sampler probably. Because we have this thing called like a back buffer in a way. It's kind of an old term. But we have like this surface that we render to that gets displayed to the screen. We need a handle for that or an ID for that, right? So we probably want to have a way to get that like swap chain image, as it's called, a surface that we render to. So we do need some form of resource handle. So we do have that sort of like, so let's include core, what we're doing, core.h here. We do have that core ID define. And these is what we use to declare our IDs, our identifier types. It just declares a structure that wraps a 32-bit integer in it. It's not anything too complicated. So this is going to be our GPU resource ID. And we'll probably have a pool of these things and we'll just allocate them. Allocate a slot out of the array or something like this. But for now, we don't really need that because we're just going to have one resource and it's going to be the swap chain image. How much experience with Vulkan? Is it worth to learn? There's lots of experience with OpenGL, but never touched Vulkan. So Vulkan is a very overcomplicated thing. If you're using the traditional triangle, traditional pipeline, graphics pipeline that renders triangles and everything, is a very complicated API. And if you just want to write a game, I recommend just sticking with OpenGL. There is also WebGPU, which is building up a lot of hype, but they do force you to use their weird shading language. But yeah, I think OpenGL is fine. And if you want to just make a game, make it in OpenGL first. And then when you have your game and it's finished, then port that to Vulkan and learn Vulkan that way. Vulkan is very manual and it makes you do lots of things, especially when you use that traditional graphics pipeline. we're experimenting with a different approach with this project where we're just going to be using compute only. So it's going to be very low level, and we're going to be using essentially the guts of the GPU, which does all the processing, the compute part of it, to do some custom rasterizing. And this is like really easy for like 2D, but it is possible for 3D. Like if you take a look at Nanite, for example, they have a custom triangle rasterizer for little tiny triangles, like sub pixel triangles, right? And it ends up being faster than the hardware that rasterizes triangles, because it's designed to be for larger triangles, more than like 4 pixels, more for triangles that are larger than a few pixels or something like this. It kind of varies across hardware, but the point is, like, Vulkan is very complicated for that traditional pipeline, and I wouldn't recommend doing it as an indie if you just want to make a game. But we're trying to experiment with something different than that to see if it is possible to throw all that complication, to throw a lot of the complication away, and see if Vulkan can be a lot more simple, right? But yeah, I just recommend sticking with OpenGL until you've got something you can port over and learn that way, because it's very manual, and it as you'll see, there's a lot of boilerplate. And when Vulkan 1.0 came out, it wasn't a perfect API. They've since added new features and made sort of newer ways of using the API, and you just have to really know everything about it, and it's huge. So yeah, like it's a big undertaking to learn Vulkan. Hey, the hostman. Oh yeah, C game engine. Damn straight. How's things going, hostman? If you're going to build a 2D game engine, which graphics API would you recommend? So if you just want to do 2D graphics, you could do Vulkan and use compute only, but you would be learning, like, it would still be a bit to learn, and there would be a bit of level. But if you're new to graphics programming, learn OpenGL. But if you fully know OpenGL, maybe you can drop down into that Vulkan. Yeah. Yeah, do OpenGL. I would do OpenGL. If you're very new, definitely do OpenGL. Funny thing about graphics APIs is they're only bad ones if you choose. Right. Yeah, it's a choice. Like, the thing is about DirectX, it's Windows only, but the new versions of DirectX are actually nicer than OpenGL. So it's really like, but they're not like massively nicer. They just have like they just are nicer. But yeah, it's pros and cons, and they're not all good choices. Yeah, see, yeah, you're making a good point there. Oh, Fly. Like when you learn OpenGL, you're not learning like how a GPU kind of works in the modern day. Like, it's really different. And when you look at Vulkan, you'll be completely overwhelmed by the API. But underneath, oh, thanks, Gabe. Appreciate it. Thank you for sub, my friend. But if you take a look at, but when you understand the graphics hardware underneath and really learn that side of things, you will see how Vulkan sort of abstracts over that. But it is very complicated on top of that, because it supports a wide range of hardware. And yeah, so it is a very overwhelming thing to learn. But we're going to go through it step by step today to get something up and running, and we'll keep doing that. So yeah, if you're interested in understanding Vulkan and how GPUs work, I recommend just following. And if you have a question as we're going through something and it's related, ask away in the channel. I'll happily answer it. But if there's some other question, there is also a Discord as well, where you can ask in there too. For stuff that's a bit more longer form or something like this. Cool. So what functions do we need in here? So we also need to initialize some form of GPU subsystem of some kind. So we're just going to initialize that there. Source GPU include GPU.h. Right. So you need to instantiate the system. That's great. We need a way to create a shader. So shader create. And to do that, we need to provide some... Wait, do we need to... How are we going to create these things? So... Yeah. So there's a shader module in Vulkan which contains the SPIRV binary. So you kind of want to have a shader binary thing, and you want to have a shader that you create from that, which is basically a compute pipeline which needs an entry point name. Yep. I think that's right. Yeah, I think it just needs an entry point name. You know what? We're just using my C compiler for shaders, so we could just give it all of the shaders, and it will just load them all up. So perhaps when we initialize the context, oh, no, we'll have a reload shaders. Yeah, shaders reload, and we'll give it something. I've got to figure this one out, but I think we'll give it like, see in HCC we've got this interrupt layer, which allows you to get, so we get shader metadata, so we can give it the metadata, and it has all the shaders with all their names, their stages, and everything. And I think we can give it the shader metadata. Shaders count. I think we can do that. So I think we can do this. Shaders count. And so we'll be able to reload. Or we could just give it a file, right? And the system watches that file and it's like it's changed and it'll reload it for us, right? So this could be an internal thing. So perhaps maybe the best thing to do is have some form of GPU setup structure which just takes in all the arguments, and it means we can just change the structure as time goes on and not have to change the function prototype and have like a million different arguments. So then we get rid of that. So I think we'll just give it a path to where the shaders are. Shaders binary. And then we'll have a shaders well, the metadata is sort of compiled into the program right now, and we don't have a... Yeah, it's only compiled into the program right now. And we don't have like a JSON file that can load it up. So I think I'll implement that sometime. Maybe we can do it on stream. But then that will mean we can reload shaders at runtime. But for now, I think this will be good enough. Maybe we just need the binary path. We need to modify that. Yeah. Right. So that'd be good. So next thing we want to do is we need a resource ID for the thing that we rendered to put on the window. So this is we probably just want a way to say, what is some people call it a back buffer. You could call it a surface. Surface resource ID. So you just call that and we'll get it. And then we want a way to like essentially record into a command buffer some dispatches. And then we want a way to submit that command buffer to the GPU and then run. And then we probably want a way to know yeah, so we probably want to you probably record like a single command buffer and then you like so typically you'll put the good abstractions do it is like using like a render graph or something like this, but I'm not sure how much of that we really want to do for this project, because I think we can get away with doing the syncing manually, because we won't be doing too much. Because another thing about Vulkan is you have to do the sync code manually. See what resources are. Yeah. So I think maybe we can get away with. We need to make some form of. We probably want to. Let's just call it a command buffer, even though it's not going to map directly to a Vulkan command buffer. So maybe you like begin. Egotist, thank you so much. Appreciate it. Thank you so much for the sub. Really appreciate it. And thank you, Gabe, as well. Appreciate it, guys. Welcome, welcome. And since you guys are subs, you can hop over to Discord, link your account, and get access to the code. Is the sun, the evil sun? How good does it look though? Oh, that doesn't look good at all, does it? Right, let's sort this out. How much better are we? It's dithering. Much better. Much better. So essentially we want a way to like record some commands into some form of command buffer. So like command buffer begin is buffer shorter? It is, isn't it? Right. Command buffer begin. We'll get back some form of command buffer, right? And maybe this will be like a pointer to some internal structure, and then we then want to say like end, right? And the word buffer is going to be used like a million times. Just every time it's used, it's probably different. Yeah. GPU programming. So when you end the command buffer, that's great. Then it's recorded, right? And it's simply just going to be an internal array. It's not going to map to a Vulkan command buffer. And then we probably just want to like have a GPU submit where we submit like an array of command buffers. So yeah, this will probably give you back a recorded command buffer ID, right? And then that can persist. Whereas this is like a temporary builder. And then you maybe you can submit multiple of these guys, right? I've got a shorthand thing here. Command buffer buffers, right? So I think this is all the API. Oh no, this is not all the API. We can't dispatch anything yet. There's no commands. But yeah, so we just need to make this, make a couple of these things here. So we're going to type def some form of these things, and then we're going to define us some more IDs. So again, we can technically have multiple of these, but we're just going to be like, there's only one, because we just want to get things up and running today and just show the core of what's going on, and then we can extend on that as time goes. Well, they're playing shirt today. I don't know, I just decided on this one. Yeah, I was wearing the other ones too much, I guess. Yeah. Time to get a couple of 300 lines of code. Yeah, it's going to be about that. Maybe more. So, what do we want to do? We want a way to dispatch, right, some shader. So we're going to say command dispatch. So everything prefixed with command means it gets recorded into a command buffer. And then what you want to do is we need our vector types, really. So U32 times 3 is basically a vector 3 of U32. This is in the maths library that comes with HCC. So we are going to end up using that. So we'll bring that over in just a minute. This would be our dispatch group, or like a group number of groups, and it's like a three-dimensional thing, because your compute shaders start they define a group size which is three-dimensional. So you dispatch number of groups across those dimensions as well. We also need the shader. So we call it like HCC shader enum. Like we generate some metadata. So going to the samples is a good. Here it is. This guy. So we generate this HCC shader enum. So we'll just use that, right? We're not doing. We're only doing compute shaders, right? So we'll just have this pre-generated. and we'll be able to launch that. And hopefully we've got enough information. So we'll see this all in a bit. But HCC shader, is it shader ID? HCC shader, excellent. So we'll pass in the shader enumeration. Yeah. So we'll get these things in. So this is going to be our initial graphics API. We'll be able to do enough to render the screen with this, but we can extend it. If we need to add more dispatches, we need to add proper sync code. We also need to have like temporary textures that we render to and all these things. But this is enough to get things going. So if we was to integrate this into the main file now, how might we do this, right? So we'll write this in, then we'll bring in HCC into the project, which is the custom compiler we've got. And then we'll write a simple compute shader, which is just rendered to the screen. And then we'll implement all of this and the backend API as well for this as well. So do a nice setup structure for the GPU. We'll initialize it to 0 just in case. And then what we want to do is set up the binary path. Does the binary path have to be passed in? Because it's custom for this game, so it's kind of a constant anyway, isn't it? Right. So we're just going to do like placeholder, because you can't have 0 size types in C. So we'll just put a placeholder there, and we will probably add. Wait, will we ever have setup code if it's a custom thing for our project? Probably not, right? So maybe we just get rid of this for now, right? It's the whole custom thing for our project, so like, doesn't matter. What about block size for compute shader? Or would it be 1 by 1? Yeah, we've gone and called them groups. Like in our C compiler for shaders, we've gone and called them groups, like dispatch groups. So a group of threads run together. Yeah, we called them groups. And when you dispatch, you talk about how many groups you're dispatching. And the group size is defined in the compute shader itself. So yeah, we've just called it that. Right, after you initialize, you probably want to... Oh, there's no way to set the push constants, is there? Shader, or we call them bundle constants. So bundle constants are basically the structure you need to upload. Where should that go? Is this the data that goes in as well? Void star BC for bundle constants, and then U pointer, I guess, for BC size. I don't know where this should go, but this is reaching my maximum number of arguments I would like, so that's good. So the shader you're dispatching, here's the arguments. Ideally, I probably want to have that to go last, I reckon. Right, that'd be good. So basically, we'll begin a command buffer. We'll end a command buffer. So here's our command buffer. We'll begin that. We'll get back a command buffer ID. So it's a recorded command buffer. And then when you submit it, see, the problem is like, yeah, I think what we want to say is like, when you record it, it will probably get automatically destroyed when you submit it, I think. I think that would be a good idea. And do we need to submit more than one command buffer in this API? Probably never. Like for this, game. We probably don't need more than one, so like why do that? All right. Cool. So what needs to go in here? Well, we need to actually do a dispatch now. So we'll call... Wait, why is it return on ID? That's wrong. Pass in the command buffer. What is our shader? Well, it'll be called something like... I know we'll probably just call it like clear, because we're just going to clear the screen. Or maybe we'll say like draw. Yeah, maybe we have a clear one, and then there kind of would be a draw one later on, to be honest. We'll draw like a box. Yeah, we need to get some sync code in. Let's just do clear for now, and then we'll do a box afterwards to get some sync code in. How many groups do we need to do? So if you're clearing the whole screen, you need the screen dimensions. So if we're doing like an 8x8 in the shader, if our group size is going to be 8x8, we need to do a divide roundup of 800 divided by 8, and then we catch it in the shader. We'll get these sizes in a minute. So what is this bundle constants thing? So what this is there will be a structure that will define for this specific clear. So we're probably going to call it like... Yeah, so we might have like a graphics prefix, which probably implements the graphics side of things. So I call it GFX for short, and probably call it GFX like we need another little short prefix to say this is to do with our shaders, I reckon. So we'll probably call it compute clear. Yeah, something like that. CP clear. Or CS. There we go. CS clear. BC for bundle constants. And these are essentially arguments that we're going to pass up to the compute shader. So we'll just say we'll add one called like destination texture ID, or texture rather, and then we'll pass in this thing here. I want to say .raw because it is just going to be a it just needs, actually no, just say .raw. That'll be fine. That would be .raw. Yeah. This is a wrap type, which is a 32-bit integer, so we're going to get that 32-bit integer part out of it. And this is going to be like a HCC texture, read-write texture, or sorry, write-only texture, which you'll see in a minute. We just need to create this thing. But so this is the way we're going to upload stuff to the size of GFX, yes, BC. So this is a small block of memory for the arguments that get set into the shader. Typically you want this around 64 bytes. You can go higher, but it just depends on the hardware you're going to be targeting. And these are called push constants in Vulkan, but we call them bundle constants because it's more of a platform agnostic name. So this is what it's going to look like from a high level. So for those who don't really know what goes on underneath, this might seem a little bit like probably have tons of questions with what is actually going on. So I think we'll start off next by bringing in making a compute shader, and just showing what that is. So at least it will clear up a lot of this, and then we'll implement the rest of it and go over the Vulkan side of things. So so the last project I was working on, which is a C compiler for SpearV. So it allows you to use C as a shader programming language. And we're going to be using this for this project because I really want to test this thing out and I think it's awesome. So it means we can just share code across the CPU and GPU, share functions and everything, right? So it's going to be really cool. So what we want to do is want to bring this into... We want to bring this into our new project, and then we want to start using it. So we have a third-party folder in the root directory of Game Without an Engine. Yeah, we'll be on YouTube. I actually forgot to record it locally. Did I forget to record it locally? Damn it, I think I did. That's not a good idea. Yeah, I've got to record it locally, but it will be going up on YouTube because Twitch allows me to export it, so that's awesome. But I wanted to do it locally just in case it buggered up. So I've got no backup now, but it should work fine. Hey, Mom. So, yeah. So we've got a third-party directory. We're going to clone our repo into there. So let's go to the super lovely, super awesome HTC repo on GitHub. It's open source. You can check it out, download it, give it a go. Yeah, highly recommend. Compile C into SpearV, which is the format that the driver takes in Vulkan. It could work for other graphics APIs, but I just need to work on that. But for now, we just want to iron out Vulkan and make sure it's all good. So we've got a project we're working on with it. So we're going to move to the third party directory, do a clone. Clone this bad boy in here. Wait, do I want to clone the whole thing? Or do I want to get the release package? And then just have a binary. Because the whole point of release package is to, like, I'm not going to be editing this source code because if I want to edit the source code, I'll just edit it, right? Like, because it's my project, so I can just do whatever I want. So in this case, I think it might be best if we simply, I need to make a new release package. Git yeah, we're going to practice using it in release mode. If it crashes, we'll fix it, do another release. Yeah. So if I run the script, the build script for release, because I've done a few little extra changes since the last release, so I want those in here because it'll be beneficial for the stream. So I'm just going to make that here, and I'll do it on the Windows one as well. So it would have made this Linux 0.1 tar. Just made this now, right? I think so. Go into Game Without an Engine, third party, drop in here. We're going to extract and auto detect the subfolder. So now I've got this. Give it a rename. So it doesn't have the Windows binary in there, but we'll merge it when we do the Windows side of things. So what has it got in here? It's got the HCC executable. It's got the documentation. It's got the sample and playground app, which we don't really need these guys, so let's get rid of them. They're just not beneficial to be checked in. It's got an interrupt layer, which we're going to be using. It's got our nlibc for GPU, very minimal, not got much in it. It's got some intrinsics for the GPU, like texture loading and stuff like that. And it's also got a mass library, which we're going to be using, that works across the CPU and GPU, which you don't have to use, but you can just use that. So let's integrate this into the project. Let's get a shader going. So as part of the core of our, what I want to include is hmaths types. So this includes all the types and everything. So I just want to change the compile flags. We'll do a few more -i, third party, hcc / libhmaths. So that will get us that included in. We probably also want libhcc intrinsics, and then we also want the interop layer as well. So I want to bring that in to our code. So let's take these, go into the build script, throw those in there. Script, build. Oh, that one. Cool. Very nice. So that is gonna, sweet. So now with this hmaths types, what is in here? Well, what's in here is a ton of good stuff. Like we've got our vector types. Essentially, we've got tons of vector types where they have like RGB. You can use an XYZ or RGB. Got kind of some swizzling going on as well. Yeah, stuff like that. So that means now in our GPU side of things, this thing now works because it's a vector 3 of U32. But we still haven't got this HCC shader thing here because we haven't actually compiled any shaders yet, or anything like that. So what I probably want to do is make a graphics. I probably want to make a graphics file, and I probably want to stick all the shaders in a single file, right? Because right now, if you take a look at our source code, we've got a GPU, we've got an OS, we've got a core, right? So I reckon what we should do is we should add a GFX C file, which basically uses the GPU abstraction to do all the rendering for the game. But also we want to have a GFX shaders file, which just has all the shaders for the game in there as well. And it's just gonna get as big as it needs to get. So I think that'll be a good directions to go. So GFX probably needs, should I put it in its own folder? Yeah, probably do its own folder as well. So let's get that going. So this time I'll do it from here, right? I was doing it from the terminal before to try and look cool, but now I'll do it from here. I could probably do that, isn't it? I could probably cat this thing. Yeah, that would be the smart thing, Valor. Yeah, that would be a good idea. Like, we could probably do that in our build system as well, maybe. That would be the smart thing. How would one do that? Cat. Compiler, compile flags.txt. So if people don't know what this is, basically Clang looks for that file. It goes up the directories and looks for that file, for stuff like in Clang D when it does this language server thing. So that's the reason why we have that file. So press F5 again, does it work? Seems to have worked, I think. So, right, we'll see how that goes. Maybe it didn't work, but we'll see. We'll test it in a bit. Man, I'm getting hungry. Oh, might get some snacks in a bit. I can feel my tummy rumbling. Don't know why I had like a massive subway, you know. But now I'm hungry again. Good old Nick Johnson. Man, it's so warm in this room. I don't like it. It's getting summer. Us Brits are never too happy with what the weather's like. Always something wrong with it. Always. Right, so we want to... Hey, Sockham, how you doing? Don't worry, the stream will be up on YouTube. Don't you worry. You'll be able to catch it on the VOD channel. It's going good, man. It's going good. We've got a window open. We're just starting on the GPU side of things now. So we're just integrating HCC into the project. How you doing? So CD into source GFX. Oh, we're in HCC there. Get out of there. That's the old project. Right. So I'm going to touch a few files. So what I want to have is a gfx.c, a gfx.h, a gfxinternal.h. So those are basically the new files we're going to have, which is the whole graphics for the whole game. Then I want to have one more, which is gfxshaders.c. And this is going to be a separate file which is compiled by the HCC compiler. And it's just got compute shaders in there. And yeah, so we'll get one in there and we'll see how that goes. So basically we open up the GFX-C and include the GFX internal H. We open up that guy and include the GFX.H. Then we open up that guy and then include GPU.H. Then we want to have something, right, where we say like render. So this is where our rendering code is going to go into actually. Well, we say like maybe it's render, and then we have an initialize, right? Render frame. Let's make it a little bit, we could call it update. People like that word when they write a game. They like to say update graphics, but I like something that's a little bit more descriptive, so I use render frame. So it's getting there, let's get in there. So we then want to go back a couple, drop those in there. Now we're in GFX-C. And this is where we will actually instantiate buffers and textures and things like this, but for now we're probably going to do nothing. What I want to do is then take this, replace it with GFX render frame, and then I want to just chuck that in there. I want to make sure I initialize the graphics subsystem, and then yeah, you're just in time for the graphics implementation. Really, we've just designed the APIs all for the GPU. So it's just very simple. We just have a couple of command buffers, and we can record a dispatch in there and submit, and we can get the surface that we render to for this screen. Very basic. So we're going to be doing the implementation in just a second. So we also want to include the GFX shaders C, I reckon. So we include the C file in here, not because we want to compile the shaders in here, but because we want to get their structure definitions. They're inside there, and we'll if-def the shaders out for the Clang C compiler. And right, so let's get going with the let's write a shader. So how does one write a shader? So first of all, we want to include all of the super lovely all right, wait. Where's the where's these lovely headers that we want? All right, so this is where we're going to put all of the, this is like a shared code section. So this is like a CPU and GPU shared section, and then this is like a GPU section down here. And here we'll simply just if def HCC, which is the custom C compiler's thing that it will define if we're using that C compiler. And here we will include, oh look, it's just got them all here. This is so good. So we can include all the things that we want. We want to have the shader stuff. Actually, no, that goes above. Oh. Crap. What about core? No, let's include standard in. Yeah, we're fine with that one, aren't we? Oh, don't do this to me. HCC maths types. No. HMath types. Yeah. Cool. So we will include all the intrinsics. All the intrinsics here. So we want some wave intrinsics. It's kind of a bit advanced from now, but we want some atomic intrinsics, texture intrinsics, all these things, all these lovelies. Yeah, I think that's good. Pixel intrinsic. Oh no, actually we don't want pixel intrinsics because we're not doing any pixel shaders. Yeah, we're not starting on the Vulkan bit just yet. We're just running the abstraction first, running the interface that we want to implement, and just sort of showing it from a high level. So if you hop into HCC again, right? It's got a samples section. It's also got a compute shader to compute a square. So what we want to, let's get standard ball in there as well. So this bit here is, we want to be shared, right? Remember we had that GFX CS clear BC, right? Which standard for graphics compute shader. So it's a clear compute shader, and it's the bundle constants. So these are the constants that we're uploading from the CPU to the GPU, so that the compute shader can use them and do stuff. So we want to write only texture 2D, and it's our output texture. So give me a moment. It's dinner silly. So remember I said your compute shader defines its group size. Well, the group size is an 8 times 8 threads, so there'll be 64 threads that run per group. And remember, we wanted to cause a clear. So we might call it clear CS. Oh, this is really bad. Maybe we can have a prefix. CS clear, something like that. Yeah. So the system values. close that. So the system values are stuff like this, right? The dispatch index. So this gives you like a thread index, basically. And you use this, like, all right, I'll explain this in a little bit. Let's just go back to where we were. So system values essentially built-ins that are provided in by the GPU, basically. Now, we got our bundle constants here. So what we can do is we can just store into the texture a color. So we get our clear color. What is our clear color going to be? Well, we'll do a red to show that we're actually clearing it, because currently the screen is black, isn't it? And then we're going to render out to the coordinate. What is the coordinate? Well, it's just dot x. Well, we've got swizzling, so we can say dot xy. So we can say dot xy now, because we've got swizzling now, so that's good. And swizzling sometimes works on CPU. You just got to get the right, like, it has to be ordered, basically. Like, you can shorten vectors really well. So what is it? Yeah, so we get the coordinate for the texture that we're writing out to, and then we write out to it. So we write out to using the store texture thing, and using the bundle constants, we get the texture, get the output texture, and then we say this coordinate, can you poke in the clear color, right? So if we go back to here, we've got this output texture now, so we can put in that surface resource ID, and then we'll be calling GFX CS clear. I'm not sure you mean by half offsets. It's not UV coordinates, it's pixel indices. But welcome to stream RCT. So there's no UV. When you're using compute shaders, there's no UVs, there's no normalized device coordinates. You're just you've got to do that all yourself manually. So there's no black box implementation like the GPU traditionally is, where you got to try and understand all the layers that's going on. Instead, you have to define it all yourself. So you just got to read the code rather than trying to guess what's going on, or having really good knowledge and understanding what's going on. So what are we doing here? So right, we're getting close to getting this in compiling now. So when you launch a compute shader or dispatch a compute shader, like the compute shader defines how many threads that run this code in one group. So we're going to say 8 by 8, which means there's 64 threads which run this group. So we call it a dispatch group, right? So there's 64 threads going together, I guess. Well, not necessarily. Let's just say, yeah, let's just say there's 64 threads that are grouped together in some way. Some of them will be executed together in lockstep, but some of them may or may not, depending on hardware. It's too much to go into right now. But you have that dispatch group concept. And what you're saying when you're dispatching it, you're saying how many groups do I want to dispatch? And because our screen is 800 by 600 in size, just as an example, we need to launch 800 divided by 8 and 600 divided by 8, because that's our group size, and we're launching this many number of groups, right? And we need to round it up. We can't have a truncate and divide. We've got to round the division up to the nearest group, right? So because of that, some of these pixels that we're going to be writing to could go out of bounds if these numbers are not directly divisible by 8, right? So what we really need is another argument to go up with it to basically say, hey, if you go outside the boundary, just don't write a pixel to the texture because you'll go out of bounds. So we actually need to have an output dimensions passed in as well, and we'll call it output dims, right? Yeah, I'm using my own compiler. That's right. So we're going to be getting it all set up. So we're just getting it all plugged in. Yeah. So we're sharing all these structures and everything. We'll be getting more functions shared as time goes. But yeah, it's going to be sweet. You also can't use some hardware parts like rasterizer and some. Yes. Yeah, I can use samplers, but you can't use this. You can't use. What's the way of phrasing it? Let's hop into the intrinsics. Okay, maybe not. You can't use the... You've got to provide the derivative yourself manually for stuff that works out the MIP level, the MIP lot, right? So you've got to do that manually. You can't depend on that. So if you're doing MIP maps, you've got to manually calculate the derivative across the pixels in screen space, right? So that's all. Which isn't too difficult. You just got to make it a function call to get you the lot level, right? Was this compiler easier to create compared to compilers for new programming languages? So I could have made a specific language for shaders, but the whole idea of this compiler was to make it for C, so I can share code and data structures, and the semantics work exactly the same, with limitations, of course. If I was making it for another language that exists today, it probably would be easier because I wouldn't have to support all the crazy stuff as... Well, okay. C is a very simple language, but there is some parts of C which are very weird to implement in a compiler. But that being said, it is... But that's coming from the perspective of someone writing a compiler for the first time. If you try and implement C++, it's going to be times a million worse. If you're trying to implement it for Rust, it'll probably be like 4 times worse than writing the C compiler, depending on how complicated the language is. But if I was to make my own language, I could have probably made it far more simple, right? But C is good enough, so we're using C. But yeah, that's basically but remember, the benefit is so we can share code and data structures. So that's fair. The bot came in. Yeah, LLVM factory, yeah. Yeah, it's a bit sad, isn't it? No one's for their own compiler backends. Yeah. So we don't support unions yet. I did have a version where we supported unions, but they require an extension to Vulkan, and it's not really supported cross-platform. So... But there are ways around unions. You can actually implement unions. Like, you can manually reinterpret data as different things. It's a bit more manual, but it's possible. Yeah, well, you can write your own backend to make it a fast compiler, right? That's always good. But yeah, if your goal is just to write a language, you just want to write a language, then like, who cares about the back end sometimes? But sometimes you do, because it improves the quality of your actual product. So yeah, it's just pros and cons, right? And obviously using LLVM might be a bit of a pain in the butt. But yeah, like, we don't use LLVM because there's no point in our compiler. Because we just compiled SpearV, which is the same level of abstractions. There's just literally no point. Right, so we need to pass in the dimensions. So we're just gonna, again, hard code this because we just want to get something up and running, hopefully today. And then we essentially, so now we can talk about this. I hate this window keep open like that. So what are these things that are provided by the, so there's dispatch group index. So remember when you dispatch so many groups from that command, that dispatch command, the index, the current index of that group, you can get that. You can also get the local index within the group, meaning like we're doing 8 by 8. Let's close this one. Yeah, we're doing 8 by 8, which means you can get the local index from 0 to 8 exclusively, right? Across the 3 dimensions. But then you can also combine those together with the fact that you know the group the size of the group, and that is dispatch index. Dispatch index is the overall index, and in terms of the way, so it's dispatch group index times by the dimensions of the group plus the local index, right? So in terms of, you can think about it from when we did this dispatch, that it is simply the pixel index, right? And that's what it's a complicated way of just saying it's a pixel index, but that's just because it's kind of low level how it's kind of low level to how compute shaders work. So it's just the way they work is all. But it's beneficial to getting fast code basically. So we'll see a lot more of that as time goes on. So anyway, that should clear the screen. So now we've got the compute shader in there. How do we get the shader enum to get made? So what we want is to essentially include some form of, like, wherever the shaders are. So I think it would be in like build, like we want to put them in the build directory, I think. So I think we can just say build / HCC shader metadata.h. So again, we don't have a JSON file yet. I really want to do this, so I could do reloading. We'll probably do it in a future stream, because it's just simply output some JSON or a custom format and then load it in at runtime, which would be a bit of fun. So we'll probably do that at some point. So we're going to be making this file. How do we make this? So we're going to be invoking our compiler. So what we want to do is run. So if I go to the HCC project, we actually have a script that does this stuff. So if we go to the third-party folder, there's a HCC directory, there's a HCC binary. I'm going to run that. Dash show for optimizations, please. We also want to say there's a file input. The file input will be in source graphics shaders.c, right? And then the output is going to be in build shaders.spv. Then we're going to say, hey, I want some output, so file output metadata in C, and I want to output some shader-metadata.h. Then I also want to enable unordered swizzling, which means that we get full swizzling support like in any shading language. It's an extension, but you just have to be aware about that. So only really use it directly in shader code, basically. And then we do this and thing to say, hey, if this thing fails, don't run Clang. So our shaders are going to be compiled first, then the application. So yeah, now if we were to run this, maybe our computer blows up. Let's see. Oh, why? No, this is really bad. Oh, we busted swizzling. Right. I will fix that. To do swizzling busted for system value. So basically, the way I implement these system values, which are like these built-in variables, the way I implement those, I had to change it last minute because it was broken on Windows on AMD, and I wanted to fix it for Compute Shader. So I've done a temporary hack. And turns out I didn't do it fully. I didn't fully suss it. So that's all right. We'll just do it this way and it'll work. Cool. So apparently it compiled that shader just fine. If we take a look now. No, we're not going to HTC anymore. That's off-stream stuff, Perry. That project is now a side-to-side project. It stays away from the streams, hopefully. Right, so now we've got a SPIRV file and this metadata. Open up the metadata. What do we have? So we've got this enum. We've got reflection information as well. I don't know why. I've done this because I want to see if it's good. We've got metadata about the shader. It's called GFX CS Clear. Compute shader, 8x8 dimensions. The bundle constant size is 12 bytes. Maybe because you might want to use this in some way. I don't know. It tells you the offset of the resources and what they are. So maybe we can do some debugging. I don't know. I don't know if it really matters so much. And there's some metadata as well. So we will be using this. Let's take a look into it. It's kind of impossible to implement all the optimization of Windows now because there's so much. I'm not sure about that. You can get most of the decent. Yeah, I think the biggest problem is like this when you like lower and lower it down, the optimizations don't just exist at the LLVMIR level. I think those are fine and those are not too bad to implement, but there's layers down to like the x86 stuff specifically, and you have to implement optimizations for that. It is a lot of work, right? But I think the reason to write your own backend is not to maybe compete and do optimizations. It's maybe just, can I do something different? Can I output code really quick? Or can I write some really unoptimized code, which just allows me to test it quickly, right? Or maybe there's some maybe you can do some optimizations, and maybe your optimizations are good enough to provide quick compile times, and catch most of the low-hanging fruit type of optimizations that you typically need when you develop a game, maybe. So for debug builds, maybe, right? So there's stuff like that I reckon is beneficial to write your own backend. LLM SPIRV backend equal bulky inheritance hierarchy, so you need that. Yeah, exactly. Like I just have to learn LLVM to just output SPIRV, which is like a really simple and great format to learn. So that's what I did. It was really easy. Well, it was easy to understand. Like the C compiler to write, I had to deal with. Yeah, it was just work. I'm an expert on graphics, but is there a good open source shading language which can be compiled to something like? Yeah, so you have GLSL, and that can transpile using SPIRV cross from SPIRV into all those other languages. But that's what I plan to do with mine. Mine actually is compatible with SpearV Cross and compiles to like DirectX intermediate language, which is what DirectX 12 uses, and it does compile to Metal using SpearV Cross, which will cross compile it over, which will transpile it over. But I've not tested it yet. And also you can use HLSL. HLSL is another language which I think the DXC compiler, which compiles HLSL, does compile directly to SpearV as well, and it compiles to the DirectX one. But yeah, I think the thing is, I didn't like those shading languages because they've got too much legacy to them, and I can't share code without doing a bunch of hacky macros. So yeah, this is the reason why we wrote this project as well. So we should be able to have this thing here. Why don't we have it here? Because so we're going to include it here, and later we'll change to interop. Oh my days, that dash is so wrong. Right, let's recompile that. I didn't like that. Underscore. So we want to do, yeah, let me recompile. Oh, shaders, plurals, please. Right, so now we've got that enum in there. And there we go. So, right, we need to have the implementation. Redefinition of, oh my days, that should be declared. We're not doing pragma onces everywhere. I always forget these. Because I barely write new files, I just write one massive file. Are we getting close? Oh yeah. Right, so that didn't work. That suggestion, someone was saying, can you run cat there? So should we echo this out? Alright, right, Windows, echo flags. Let's try that. Right, problem is it's got new lines in it. That's the issue. So, can I get it to... I need to sh strip new line characters. You can use sed. So pipe tr-d trim, I guess it means. So if we were to say take that and then do that. Oh ho ho, so we want to put a space character. No dash d then. Bam, that's what we want. But yeah, obviously if we do this in C, we just write that. Oh, did we not do the dash L X11? Wait. Oh, maybe we don't need that. Yeah, maybe I just didn't include the X11 thing. That's probably just me being dumb. Oh, okay, it was me being dumb. Okay, I don't need that. That's fine. Right, so we haven't actually implemented the GPU functions yet, right? So should we do that? So all of these guys. So, you know, we're not going to actually implement these yet. We are going to, yeah, we'll open them up. We'll put something basic in, and then we'll get it compiling, show that it runs, and then we'll so put a 1 in there. And then you want to return a null. Oh my days, get it. Maybe we do include the standard lib, I don't know. It would be nice if we didn't have to, but I think you need to include standard lib. Standard def, okay, so that should be a smaller header. Again, we're only having one command buffer, but we'll store that in a sec. Unused parameter, core unused, command buffer ID. Oh my days, these are all unused. Shader, num groups, BC size. Okay, hit compile. Nice. Does it run? Here's our black window that we saw before. Obviously not rendering anything because we've not done any Vulkan code, but we've got a GPU abstraction there. We've got our shaders shader compiling. We have our graphics interface, which we'll call our GPU interface, to record it, start command buffer, dispatch our compute shader, and then it's going to end it and then submit to the GPU. Cool. Let's have a bit of a catch up. As a web developer once, once in a while I take a look at computer graphics, the complexity, the maths, and the challenges that are not. Yeah, but doing web dev makes me feel like I'm just not sure when it's boring, something like. So I was really bored as a web developer. I didn't want to do that as a career. Worked on it for a bit. I did some C# development and stuff like this professionally. That's what I just fell into because around where I live, that's just the thing that has jobs. And getting into the games industry is not necessarily an easy thing. And I always wanted to make games because it is fun. I like writing engines. I like writing things from scratch. I like writing things from scratch, and I also like having a visual feedback every now and then when I write code. I like to be able to boot it up and see a thing, right? Because like that, there's something about that. So I think games is a really good fit for all of those things. Unfortunately, the industry is sort of going towards, in general, going towards not writing your own technology. So this is part of the reason why I'm doing this and documenting it, is because I want to show that it is possible to do such thing. Write your own technology, write your own game without an engine or whatever. And it's possible. You just have to understand the things underneath. And when you write when you use other game engines, you should really learn the stuff underneath anyway, because then it helps you make a better product. But going back to the original question, to me, working as a web dev, and that was it was not really compatible with the way I viewed things, and I felt like it was basically poisoning my way of thinking when I was working as a developer. So it really threw me off the idea of working. So it took me a long time to get into the industry, but when I did, it was much better that a lot of that stuff is gone. But yeah, you don't have to get into graphics development. You can be a gameplay programmer, and you still need to learn a bit of maths, but it's just linear algebra. And typically, you just need to learn the linear algebra and just know how to use it and apply it. And it's not too hard. Sometimes it gets you, a bit to learn, but it's nothing too bad. But yeah, just if you fancy like doing game development, just give it a go, because I think sorry, if you fancy doing game dev because you want to learn more about the computer, you can always start off as a hobby, and if you feel like you want to do it full time, you can go and chase that, right? So if it's in your hobby time, it's always easy to just stop it if you don't like it. It's not like you've made a whole career change or put in all this effort to actually solidify that career change, right? So that's my thoughts on it. I made an SDL engine with C++. That's cool. Yeah, that's another thing you can start with as well. You don't have to do it completely from scratch like I'm doing here. You can use SDL. It's a good way to get up and running, especially if you're new to this sort of things. But graphics engines feel useless when Unreal and Unity dominate everything. Not really. Like, yes, that's the thing. The great thing that's been suggested by Toggle is like you have to work with their tools. Like, do you want to work with their tools? Like when you have everything set up with your custom tools, and you build something specific for your needs, you'll notice that, hey, my project can just compile instantly, basically, or pretty much instantly, or I can reload my game like this, or I can, like, there's pros and cons to each direction you take, right? And you just have to leverage your pros. In terms of income and career, I'm not sure. Like, if you look at the state of the industry, most people don't become engine developers. So they'll probably be in quite high demand. So you could possibly get paid more by knowing something that not many people know, and being an expert at that. So as an individual who works for a company, you could actually earn more, right? And have a better career. Like, it just entirely depends on the way you look at it. Like, but if you want to make a product and you just want to make a game, and you just want to make a game and you don't care about the craft, you can just use Unreal and Unity. Like, it just entirely depends what you want to do. Like, But for me, I enjoy this. I enjoy this side of things. Right. So what's the next plan? The tools are to cut out a lot of development time. Sure, but they're tools to just solve a certain problem. So if the problem isn't solved by those tools, then it doesn't really cut out development time. Right. So what's the next thing we need to do? So next thing we need to do is actually implement recording into, so setting up the graphics side of things. So we'll be doing some Vulkan now. So let's start by just doing the initialization, I think. Yeah. We'll start with that. Right. I want to take a quick break. I'm going to get another tea. I'm going to get some snacks. I'm hungry. And then we'll start creating this Vulkan instance and setting all those lovelies up. And we'll be referring to the HCC samples because we already have a thing anyway, and we'll be talking over all these things. But yeah, I'll be back in a couple of minutes. Just gonna make a tea and get some snacks. So enjoy the tunes. Alright, welcome back everybody. So I got me some nuts here from Asda. Probably destroy this whole packet, you know. So, right. What's the plan? So, basically, we have this gpu.c file, and we're going to be doing some stuff in here, maintaining some state of some kind. Let's get this thing sorted out correctly. We're going to be managing some state. Pragma once, all you. Sweet. So we're going to be like probably checking. We'll probably be having some assertions on the parameters, probably managing some state, and then calling into the backend to do backend specific stuff, and then returning back, and then maybe doing something afterwards. You know, so we'll be basically like wrapping, like some of these are just gonna have like a simple backend initialize like so, but others might be more complicated, and like the API is not going to be one-to-one. It's going to be a bit different sometimes. So call back and initialize here, and we'll get to these other ones in a bit, but let's just get things set up. So we have a backend initialize. So this is our backend API, and each backend is going to implement this. So we have a Vulcan one. And then so pragma once, and then we want to include the wait, which one includes this one? We can probably include GPU here. GPU internal. Excellent. So yep. So this is going to include GPU Vulkan internal. So all the 4 definitions go into there, and we just need to implement this guy for now. So basically we want to have a global structure, type def strut GPU Vulkan, and we're gonna, you know, in true well, this is just what I do all the time, we're going to declare a global variable. So GPU Vulkan, and this is going to have all the Vulkan bells and whistles. So what goes in here exactly? Nice. So the first thing we need is a VK instance. So we need to include the Vulkan header here. So here's the thing. People will have to install the Vulkan SDK on their system. And this is like This is not good. Because it's another barrier to entry to people downloading and using the code. If they have to get every single dependency that this project has, which probably won't have many, but it's still effort. Also as well, if we have a bug and we need to rewind go back in the history and see, go back in the history and compile the code base, we'd have to wind back our dependencies as well on our operating system. And it doesn't seem like the desired behavior that we want. So a way around this is to bundle the Vulkan SDK in with the with the repo and any other thing that we need, basically. So you can just download it. So it's installed on my system, but it just means people don't have to install it that way. And it'll just be a lot nicer. So just on the tar file. And download that. Open this bad boy up. What's in here? Quite a lot of stuff, apparently. So we want some of these include files. There's some binaries. It even comes with like DXC and everything like this. One day it'll come with HTC, I swear. But yeah. We probably want where are they? Lib, I guess. Yeah, so we probably want to bring a lot of this over, but I'm not sure. So the layers aren't in here. I don't know if there's any Vulkan layers where we... Are the layers.so files? Might be in lib then. Ah, yeah, they're there. Good. Yeah, we get these layers in as well. Excellent. Right. So bring a lot of this in. So go to our third party thing. Create a Vulkan directory. You'll need one per platform. Yeah. So it's fine because we'll be able to merge it. It won't be an issue, just merge it manually. So you just say x86, right? So we should probably note down what SDK we've done. We could just drag that whole folder in. It's 2.8 gig. A lot of bananas. So we'll take a lot of the crap out, because I don't know if there's that much room. Lib. Where's all the gigs coming from in here? Gigabytes, gigabytes. Oh ho 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 ho. The Kronos validation layer is 1.8 gigabytes. Oh ho ho. What the crap? That's a pain in the butt. Yeah, I don't know if that's a good idea. Maybe we get them to install the layers on top. I didn't expect it to be that big. That's a binary. They've probably got tons of strings in there, but that's huge. Like, it's a real pain in the butt. Like, we've got Git LFS, right? But we've only got so much storage. And I don't know if that's going to be a good idea to do. But it would be good to, like, bundle a lot of this in. Like, for now, I think we'll just put the include files in. And I think... You know what, for now we'll just say you have to include it in your system. Like, I don't know a good solution for this yet. We'll just say latest Vulcan. And we'll try that. But that's annoying. Like, I can't believe it. It's one of the biggest binaries I've ever seen. 1.8 gigs. Huge. Right. So ignore that one. We'll just park that problem off into the future. So we've got it installed on our system, right? Via the package manager. On Windows, you just download it. So we include Vulkan core.h, and then we're going to use vk instance, and we'll do vk instance. I like to prefix everything with vk when I do these things, because, you know, you might have a buffer, and it's like, well, is that the Vulkan buffer or something else? So I prefix it always vk. So, right, got a global variable. So a vk instance is the thing that you make first when you initialize anything Vulkan. Basically, an instance is when you destroy an instance, everything that has been created using that instance gets destroyed. So yeah, it's just it's essentially like our global. Essentially, it's like our global variable here, right? For this thing, it's like the whole context for the whole Vulkan thing that you're creating. So how do we do that? Well, I made one earlier. Don't get that one. So samples app. Oh, there's so many juicy bits in here. So yeah, it'll be something like this. We'll make something like this. Ooh, VK. Ooh. I can make it smaller. Let's do it. All right. So what's the plan? So we'll copy this pop, one by one. All right. Let's explain what's going on. Okay. So what is this doing? Right. Fine, let's do what Perry suggested earlier. Maybe not. Bad idea. I did it, Perry. Thank you, Perry. I do take your suggestions. All the time. Just, they might be a bit delayed. You know, as they come around. So, okay. Most functions in Vulkan return a VK result. So we just stick it up here, and we have a super lovely handy dandy macro. So in our internal thing, we're going to make this thing. We'll call it GPU VK assert, and it's going to use our core assert, and it's going to use the VK result that's just defined on the in the function scope. It's going to set it to whatever the expression is you pass into here. So you wrap your function calls in that. If it's not a success, it's going to say Vulkan error, puts the string of the expression in there. So if it's a function call, it just strings the whole thing. And then it says returned from file and line. Does it have to do file and line? That's the whole point of an assert. That's the whole point of an assert. It has the file and line in there. But I put that in there because it wasn't part of that sample application. Didn't do that. Right, and then we have a simple thing, GPU result string. Nice. So that's a nice function that'll help us out a lot. VK result string. One of these. I need this guy. So there is a header that declares this in Vulkan, but it's for C++ only for some reason. So we've just made our own. So it just takes a result in and returns a string. So the results just look like this. Basically, the 0 value is success, and anything from 0 and positive is a success code. Anything negative is an error code. So we just have a string version of all of these, right? There's not so many. So, right. GPU GPU VK dot VK instance. Nice. Core name, application name, game without engine. Now, why don't we have this as a global variable somewhere, right? Why don't we in our core at least, because it's just included in everything, why don't we define the core application name? Okay, a bit too long. Core game name. Game without engine. So that's what we're going to roll with for now. We can obviously change it later. It's just all here. So plop that in there. Application version. 0. Engine name, we don't have an engine, right? It's without an engine. So we'll just repeat it, I guess. We want to use Vulkan 1.3 because that's what our compiler, HCC, kind of requires. And there's some good stuff in Vulkan 1.2 as well. 1.3, yeah, it's the latest and greatest. Let's use it. So now in Vulkan, typically it's got very it follows like the API follows a lot of similar rules. There's not too many inconsistencies in Vulkan API, which is nice. So things are in structures. But the instance one is, yeah, so the instance is kind of one of a kind in a way. But yeah, so usually the first parameter is like a handle to like an instance or a device. But because you don't have an instance or a device yet and you're creating it, you kind of miss that one. Then the second one usually is a create information when you have a VK create something. So it's create info, it's just a structure of arguments. And then there's this allocation callbacks, so you can have custom allocators for the CPU side. None of this is GPU allocation. It's just if the library internally allocates memory, you can provide a way to custom allocate that memory. And then you get an out parameter for the instance that you're creating. So that's basically the way it rolls. Again, it returns a result. So basically, if it errors, we will capture that and then assert. So we've got the assert there. Cool. And then this string will be printed out as part of the assertion if there's any problemos. So, rightio. Why don't I see? Oh, it is good. So, yeah, that's how you create an instance. But what is all this stuff that we're passing and what are we doing before? So when you create an instance, there's a few things in Vulkan. There's layers and there's extensions. Layers are essentially a way of saying, if I were to call a Vulkan function, a layer can intercept that and it can do something and then call the lower layer. So it can intercept the data. So that's how a lot of the layers work, like that validation layer and the other layers, is they simply intercept the calls, they track some information, and then they report errors if need be. So that's what layers are. Then extensions are, now in Vulkan, right, there's tons of ext whatevers, right? Oh, days. Yeah, functions with like ext on them. That means they're an extension. There's also other suffixes, but in general, they're like this. So to have access to these, you need to explicitly say via a string when you create the instance or a device. I'm using this extension. Now the extensions and layers are for devices. Nowadays. Yeah, so the devices or for instances, there's instance extensions and instance layers, and there's device extensions and device layers. We'll get to the device bit in a minute, but a device is basically your connection to the GPU. And it's a way of referencing that. Right, so we basically, like up here, we query for these instance layer properties. Now, this is not really a good way to do it. 2D temp allocate this, because this makes a stack. It just requires a big stack. But maybe it's fine. So we essentially ask Vulkan, hey, what is all the instance layers that you have now? And then we enumerate over them. We try and find the Chronos validation layer. If it has it, we want to use that one. And you don't really want to use this in debugging because the validation layer is really slow, because it does tons and tons of debugging allocations. If you suggest, I'll go to bed and I'll take your suggestion. Yeah, man. I'll catch you in a bit. But yeah, thanks for coming, and hope you enjoyed the stream. I'll see you in a future one, Toggle. And yeah, also really enjoying the podcast. Keep it up. Yeah. Hope you have a good one. Thank you, sir. So this validation layer is typically quite slow, and I think it does tons of like allocations internally. It's very dynamic, so it really cuts the frame time down, unfortunately. So you only really enable this when you're developing the graphics code. And then this debug utils one is very useful for when there is a Vulkan error by the validation stuff. This extension is very useful to be able to set a breakpoint when this happens, and then you get a stack trace and you can look through a debugger, and it's very helpful. So we enable this extension as well alongside it, and we search for these extensions, and we do this. So we have possibly two layers. One is validation and the other one is API dump. So this one is really good. So it basically, every function call that you make in Vulkan gets dumped to the terminal, and you can just see its contents, and it's super handy for debugging. So yeah, we enable that one if we want it on. And the extensions we enable here of BKKHR surface, which basically is saying you want to do graphics with a it says you want to render to the screen. Basically, you need that extension on. Then you need to enable the specific surface for the specific surface for the platform. So if you're using X11 and your Xlib, you're using Windows, you Win32. Now, I think I want to have some custom defines here, because then it's just consistent and something that yeah, because it's consistent then, right? Because it's just so hard to guess these sometimes if you're not really very familiar with them. Core OS Windows. So there you go. So we're going to say, hey, if Linux, if defined Linux, and then if defined Windows. So we then enable this. Ta-da! So then we enable the specific extensions. So we've got an array of strings for layers and extensions to enable inside of the Vulkan instance. Then we have debug utils, we attach that one on as well. Nice. Now we have this app info, which basically says our application name and version and so on. Then we attach all the layers and extensions and the app info, pass that in, which is the create info, and then create the instance, right? So let's print out here and say created instance in the terrible spelling that we just did that in, just to prove that this actually works. Include me some standard IO, please. We might do some, so to save including standard IO, we might have a custom printing thing in rather than printf, because it's just a lot of effort to keep including that all the time, and it would just be good to not include standard library for everything. So does that compile? Well, it doesn't compile apparently, because it doesn't have, we don't link to this. So we're going to open up these compile flags and do -l Vulkan. Give it a compile. GGPU did extern. Your first time here, what am I looking at? Hey there, Mr. Carson, how you doing? Welcome. We're currently writing a game from scratch with nothing but C, Vulkan. We're not using a game engine, we're just writing our own game without an engine. We currently have a window open. We've got some events. We did this all today from scratch. Got some key presses. Got a window that does nothing. And we are currently getting Vulkan set up. And yeah. Awesome, good to hear. So we've also got our own little custom C compiler that compiles shaders. So we can compile shaders in the C programming language and share code between the CPU and GPU. So we've got our own little graphics API that we've written, and we're just writing all the low-end Vulkan code to sort of get that working. So we're going to begin, when we render a frame, we make a command buffer, run the clear compute shader to clear it to a red color, and end the command buffer and fire that up the submit that to the GPU. Yeah, so this is the this is what we're doing. So we're just running the Vulkan code right now. Oh my days. Standard string, I need that as well. See, I would really like to limit the standard library to like 2 files, to the operating system and to the core file, and then the rest of it doesn't touch it. But we'll see how that goes. Right, so do we compile? Created instance in this terrible language we just came up with, but it worked. Right, so we create a Vulkan instance, the game runs. So that's cool, right? Yes and no. So the way we're implementing this right now is okay, but there's a problem when we call, well, not specifically this function, but maybe other functions in the future. When we create the device, you know what? Let's create the device first, and then we'll talk about this thing I've just spoken about. Maybe we'll save this for the next stream. But yeah, let's hook up to the GPU. So we're going to go into the other one of my previous examples. create devices next. Take this with us. Right, let's take all this, drop it in here, give a bit of a refactor. Oh, validation handler, eh? Ooh, this is good. Like this one. Drop this down here. GPU VK handle validation error. We'll drop that there. Oh my days, there's a whole big thing in it. Right, this is a callback. So remember that debug utils extension we had? This is basically it. It complicated Vulkan stuff. But yeah, so essentially when an error happens, a callback, you get a callback, and we log this out to the validation error thing, and then we display some message box apparently. That's cool. We'll probably implement that in a bit, but let's just go up to the top. I can't believe the Vulkan SDK is like 1.8 is like 2 gigabytes rather. It's just insane. Right, so after we create the instance, now it's time to create like a debug utils messenger, which basically sets up the callback and say we only want it for errors and for validation stuff. So yeah, let's set that up. GPU. You know what? We should look for GPU dot GPU VK dot GPU VK dot VK underscore. I think that would be good. That'll do a lot of things. Right. So we're doing this to create wait, what's the prefix? GPU, no. Yeah, GPU VK. Nice. So this like loads a function pointer, the extension function pointer specifically for VK create debug utils messenger extension. It loads that, we call it, and then pass in the actual create arguments, and then it creates this messenger thing. So now this callback will get called. So we have down here, which handles any validation errors and writes out to a file with a lovely stack trace. Next up, oh, this is so bad. Right, to do temp allocator. When we write a temporary allocator, we're going to come through and correct all of this. GPU. So the plan here now is to start making that connection to the actual GPU. Now you get to choose, which sounds great, but it's kind of extra pain in the butt. So this code here basically it just picks the first one. So if you're running this on a computer with two or more graphics cards, you may or may not get the one that you want. Like you might have an integrated GPU and then so really you should go, like, you call this function here to get all the physical devices, then you should enumerate over all of them, get all their properties and have a look at what you want and then pick the best one. But we're just going to pick 0, and this is not good code in any way, but it starts things up. Then we get some memory properties. Okay, we'll get those. Memory properties. Device memory properties. That's what we want. Yeah. Roll with that for a bit. So the memory properties tells us like how big are the heap? How many heaps are there? How big are they? What are their memory types? So you use this later to allocate memory. So you can, but it just means that it's extra work right now, and we just want to get something up and running. We will take a second take over this, but we just want to do a bare minimum. And you can't really check which is the fastest. It is a real pain in the butt. All you can check is which one is what extensions it supports, what is its features, what are the limitations of the device, meaning like really weird stuff like, oh, what's the maximum buffer size, what's the maximum like memory, so what's the maximum number of I'm doing a really poor job of explaining that, but there are some limits basically. And what sort of properties of the physical device are there? So properties meaning like their memory, their what's the number of descriptors or something like that per stage, like things like this. You can also like, so the only metric that I know about that I use is I take the memory, I see how much memory the device has device locally, so on the GPU itself, and I use that as a metric to say how good the card is, right? How much RAM has it got? It turns out it's probably a good metric, but also I tie it in with some extra things to say, is it a discrete GPU or is it an integrated GPU? Because there is an enum for that. And if it's a discrete GPU, it basically gets the biggest priority. But yeah, I typically just use the memory to tell which one is better. First discrete card works well for normal PCs. Yeah, you can use that too. That's another way of doing it. Yeah, that's probably a good way. That's probably good enough, isn't it, for most PCs? But if people have like multiple cards, so effectively you always need a way for the user to manually select the GPU that they want. And obviously still check it to see if it's compatible with what you want to do in Vulcan land. So yeah, there's that one. So memory properties is basically, again, what are the heaps and that sort of thing. Format properties, we need this for our HCC thing. So any texture type that we use, we need to double check all of those. Oh, Vulkan is so bad. Yeah, so because in HCC we don't specify the format when we use textures, we have to check if it has compatibility up front using this thing. So we'll have to check that for all devices at some point. So this one just checks it for RGBA textures. Right. So this is me selecting a physical device. Again, not the best way of doing it, but it's something. So if you're running in this, you must change this number here. Yeah, we'll make that better in the future. Queue families. So a queue is what you submit your command buffer down. So your command buffer is submitted down a queue. So we just need to open up a queue. So all we need is a queue. Oh, I want that macro. We haven't done any for loops yet, have we? We need a good macro for that. Index, start, end, for, u pointer, index equals 0, index less than start, oh sorry, wait, sorry, index equals start, less than end, index plus equal 1. So that just makes it nice and easy. Then we'll have a signed version of it. Typically they're like that. We'll add the sign whenever we need it. But yeah, it just makes it easier to work with. Sim for loops is just long. No member named. Right, so we select the queue family that we want. I don't know if we need any like 2 or more queues. Like, we will need some queues. We might need like a main queue and a transfer queue. But I don't know if we need anything more than that. Right, see you later, everyone. It was Hannah. Thanks for coming. Yeah, man. Have a good start to your week. Yeah, good work week. I'll see you soon. Thank you for coming. So when it comes to these queues, I guess we'll just keep it simple, right? Don't overcomplicate it. U32 VK queue family index. Yeah. So we're looking for a. See, I'd like to have like a U32 max definition. Sort that out as well. We want to define like uint or U32 max as uint32 max. Just shorthand it, make it nice. 8. 16 and then 64. Signed ones first, please. And then they obviously need the mins. Min. Oh, buggered that one up. There we go. So we've got some like shorthand things, which is nice. U32 max. Cool, so all of that seems to be compiling now. So we go over and try and find one with graphics and compute, but again, we're not using the graphics features of Vulkan in this. Remember, we just want to use compute only. So I think what we want to do is specifically look for so if you read the Vulkan spec says that a GPU, if it has graphics, there will always be a queue with graphics and compute. Yeah, there'll always be at least one queue of graphics and compute. So what we kind of want to do is we want to like we potentially want to ignore that queue if there's no async compute queues. I think that'd be the best shout. So we typically want to like try and look for, you know what, let's do this. We say if if it's still equal to that, let's just go and get it proper. So we're trying to make sure that it does not have graphics and it has a compute bit set. Let's take a look at these. Yeah, we can't rely on it. Yeah, so we have to do it like that. So we're typically just trying to look for async compute first, right? Try for compute only queue first, and then if we failed, right? Failed to find compute only queue. Let's settle for a graphics and compute queue. Then if not, we settle for that one. If it doesn't exist, we'll just do a Hey Soulfoam, how you doing? Yeah, man. Moving on to the next project. How's things going? Good to see you. So yeah, that's what we'll do there. So we need to select our queues in the queue family. So we might in the future have multiple queues, and the reason why you'd have multiple queues is if you'll have your main queue for like the game that renders each frame, but you might have some other work that you want to run alongside the game that takes a longer period of time. Maybe it runs you want it to be scheduled on the GPU that runs maybe alongside your game frame, but maybe it runs over longer periods than an actual frame, and you don't want it to impact your actual. So you think of it as like threading in a sense, but it's not really. It's like it runs independent of the other queue, and you have to manually sync over it. But yeah, I don't know if we'll need that for this game, but if we need it, we can always add it in later. So yeah, we're just gonna have one queue right now, and again, if we need async transfer queue, we can set that up later as well. Not a big deal. So we're just gonna go ahead and create a single queue by having this queue create information. Good man. I had to get away from programming for a few weeks. Was getting super burnt. Yeah, man. I know what you mean. Yeah, I took a week off. We only just started today. But yeah, it's good. It's good to take breaks. Stop thinking so much, you know. Not very much. Don't say. Refresh now. Ready to. Yeah, awesome. Good to hear. It's good to go outside. Don't have it very much. It's so negative. It's funny. Yeah, it hasn't improved, but it's fine. It's good enough as it is. Programming is great as it is. It's so much fun as it is. Right. So we have this queue create information. We basically specify the family index. So what is a queue family? A queue family is basically like, we just search for this queue family. And it'll basically, we found our queue family where it supports compute, and a physical device, you can check its queue family properties, and it tells you in there how many how many queues does the family have? So if you want multiple queues and doesn't have them, then it will fail to create, right? So that's something that if we have more than one, we should check that. So what we're doing is we're just saying create one from that queue family. And then what we're saying, oh my days, here's all the super lovely Vulkan feature stuff. So we're about to create our device, and so that we've got a physical device, but we need to now create a connection to that, and that's what VK device is. It's a logical device, as it's called. So we need the queues are created with that logical connection. And also we need to enable features with the device. So what features are we using of Vulkan? What extensions are we using? Stuff like this. So we're not using dynamic rendering. We will be using synchronization too. Shaded demote to help invocation. That's something you need to use in HCC. Maintenance 4 is good to have. Vulkan memory model is needed. Like all of these guys are needed with HCC. So our custom C compiler, all of those are needed. And so we just chain, this is like classic Vulkan. If they need to add anything new, they will daisy chain structures together. So you declare a structure in Vulkan, it has this S type to basically tell you what type the structure is. So they can cast to this type in the driver when they see this enum. And essentially you daisy chain them all together. So features here has a next pointer to 1.1, which then has this S type and this P next. So they just chain together and they have basically a header of the structure they can check. And more extensions could be added in the future because it's the same format, right? It's just an enum at the top to say what type the structure is and a next pointer. And the type of the structure will allow them to dynamically cast it into the right type and use all the future members for what they want. So from features, it's all daisy chained together. All these features are daisy chained. And when we create our device, features is passed in as a pointer into pnext. So yeah, that's just how it all works. So what extensions are we using? We're using a swap chain extension, which basically means I want to render to a screen. And a swap chain is a way of getting a bunch of images that get swapped out to the screen, stuff like this. So you need that extension. Basically every device supports it. And then we core GPU. Then we create our device that goes in here. VK device. So what game am I making? Did I see that question? Sorry, I didn't answer that. So we don't know what game we're making yet. We are spending time doing some R&D on what is the graphics / art style that we want for this game. We're going to see what sort of like unique things that we can come up with and what benefits and disadvantages this gives us. And then we're going to design a game with that in mind, along with other things. Yes, that's the plan. So we're just going to start off by doing some experiments, R&Ds. So this gets the queue. So after you've made your device using VK create device, you can then fetch the queue handle because it just breaks the API if they returned it out in some other way. So they have a way of fetching that. So the queue is what when you call VK submit and submit your command buffers, you submit it down a queue. So there's our main queue, and again, if we have more, we'll make more. Nice. So again, we're just going to then print out to the terminal. We're simply just going to print out Like, success is something like this. Does it compile? No. Because all this stuff down here doesn't. Nah, 3Ds, my friend. Why isn't that stack trace included? Was it included with the... Oh no. B stack trace, yeah. Ignore count or ignoring? 2. So we make some log file again. I've got to really abstract this stuff nicer. So I think when we get everything together, we are going to do a cleanup and sort of before we write more code, because the worst thing about refactoring is the more code you write to clean up, it just makes it big of a task. So you want to I think we want to find a lot of the things we want to clean up, and then take our time and actually do that. So anything in future that we do, I see this file thing is just so specific for these platforms. We'll sort that out, sort all these other things out, like printing and everything. This message box, we don't have a message box yet. We'll comment that one out. And then these raise and breaks. This will be handy as well to have. Can we break? No, we can do that in the header. We'll find it. I'm running GSL version tester application right now. Compile shaders across all APIs such GSL version combinations. I mean the weirdest bugs. Oh wow, crazy. That sounds nuts. Yeah, every surprise because you're coding. Wait, what did Solfam get when you see USC? Oh well. Anyway, that bot is going AWOL. Maybe some voxel ray trace stuff for compute. Well, maybe. We've already done a custom voxel ray tracer here. These are actually very tiny voxels. You can't really tell. But yeah, I don't think I want to do something like that. I don't want to use voxels. I don't. Yeah, I don't want to use voxels. Or triangles. Because I think there's too many people doing voxels and triangles. Do something different. But yeah, I'm holding that as a secret until we do it. So, in the GNU platforms, is there a GNU debug break? What are the intrinsics? Built-in break. Built-ins. I think is there built-in to break in the debugger? Built-in break. built-in cannot be used as a breakpoint because the optimizer removes all subsequent code. No. Yeah, those are unrolled triangles. When I did unrolled triangles, no triangles are all banned from the code base. It better not do raise SIGINT. Right. What we got? Built-in trap. Maybe we use this trap thing on Linux. Let's set it up. So this allows us to like programmatically break inside a debugger, which is like super handy. Should be used everywhere basically. So if defined, then we kind of want to say like else if defined Windows. I think Windows has a way of doing it. Yeah, maybe she's the trap. Here we go. Debug trap for some versions of client. And you want debug break for MSVC. Oh. Yeah, because they don't have like inline assembly in all compilers, so you got to do it this way. Define core debug break. Call it breakpoint. Core breakpoint. Core breakpoint. Debug break. There you go. So that'll be super nice. So we can essentially just use that in here. Whenever there's a Vulkan error, be amazing. So let's hit compile. Compiles. Hit run. Successes. So we've got a device we've connected to. Nice. So should we see this thing in action right here? Right, it will open up and throw out. So what happens if we were to provide null for these extensions, right? What does it do? Does it fail? Oh, it just doesn't like it. Let's pass 128. Excellent. So we hit a trace. So we should be able to open it up in the debugger now. When we run it. So Vulkan takes a while to boot up for some reason. It just does. There we go. Finally it boots up. We see this here. So we see in VK device it failed. It goes through the Vulkan validation layers. You finally hit this and on our core breakpoint. Right. So that's really handy programmatic breaks. So we can see exactly in our code what is the state of everything. We can log it. It's really nice. So another thing that it does is it logs out a file called, wait a minute, game without engine, VK validation log. And notice here, it's given us the stack trace and the error, the exact error. So again, that's really handy as well. We probably want to print some of this out actually, but yeah, I did this mainly for users, but I probably want to put it out in the terminal as well. But yeah, super cool. So that's got us, yeah. All right, so let's hop into here. So that's got us a device now. So the next thing to do is probably create some shaders. You create the shaders and create the pipelines. What else do we need to do? Oh, you need to make the descriptor sets. Yeah, stuff like that. Right, so some renaming here. What else have we done? Yeah, also added the whole GPU, GFX side of things. Update the build script and the command line arguments. So just going to commit this to say that we have all this change. Done more than that today as well. Right, so we've simply we've sort of like add like initial GPU and GFX interface and Vulkan device creation. That's about as far as we got with that one. So I'm going to push that. Let's log into bash because I've got to do that silly thing again, isn't it? Git push you up. Oh. So it didn't work. Huh. Right. So you should find that up on the repo now if anyone's interested in taking a look. Cool. Because we deleted all the images, didn't we? No images. Oh, it's PNGs. Oh, we did the PNGs. That's fine. That was close. Right. Awesome. So for those interested and who are subs, who are subbing on Twitch or via Ko-Fi, you can access the code. Take a look at the Discord channel there. You're going to take a look for the descriptions. I don't know why. What is the GPU Grand Prix? No, it stands for general processing unit. It literally stands for general. processing unit. You think it was stand for graphics, but I'm pretty sure it's general. Oh no, they say okay, it is graphics apparently. I'm pretty sure I've seen it and it's the general processing unit. Yeah. Weird. Hmm. Yeah, the Grand Prix unit. You heard it here, folks. You heard it here. Right. So, we didn't get as far as today as I wanted. I was very optimistic to get a compute shader running, but we did make good progress today. We got a window open, explained all of that as we went. We started to do the Vulkan side of things, we designed our graphics, API and everything. We've brought some, there's still lots of utility stuff to do, but overall it was good. So we did about 634 lines, which ain't bad. Bear in mind I did copy and paste a lot of it, and edit it, but that's a good day. What other commands do I have? I don't have all my things on here. That's annoying. But yeah, if you guys missed this stream, want to go and watch it back, there is a VOD channel you can go and watch it on, which will go up there as soon as I can get that up there. What else do I want to plug? There is a Twitter where we'll be posting, I guess, my progress. Dude, I'm so glad you're using Brave. Recently switched so much faster than Chrome and Firefox. No idea. Yeah, I don't know what it is, but yeah, it's just so much nicer because you don't get any ads. Like, ads basically ruin the internet, and I know you don't get to support websites that make, but it's like, yeah, like they literally ruin the internet. So like, if they didn't ruin the internet, I wouldn't want to block them. Like, it just makes it so bad. Like, so yeah, I think Firefox is pretty much toast nowadays. Yeah, so in the next stream we'll be finishing up the Vulkan side of things. We're going to get descriptor sets in, and we'll talk about what descriptor sets are using bindless resources. We'll set those up. We'll create our shader. We'll create our graphics pipelines, which is basically our shaders. We'll then create our command buffers, and we'll record into the command buffer, and then we'll submit that to the GPU, and then that should be something rendering on the screen. After that, we probably want to, like, the stream after that will probably be a Windows dev stream to sort of like port it to Windows. But I might hold up on that to maybe do a bunch of utility functions and really get a list of things to port to Windows, then go and do it all in one stream and port everything over. But yeah. Let's find somebody to raid because I've got a jam. Gonna go and relax before bed. But yeah, thank you for coming, everybody. Find someone to raid. Where's some programmers? How does one find programmers? Other day I found content below signed up cookie burners. Oh yeah, they also get rid of the cookie stuff as well. Yeah, they get rid of the cookie stuff. It's really nice. Like, just using Brave basically makes the internet feel more or less like it was before all of this terrible stuff came on it. Right, I see Asm. Let's raid this dude. Right, so the next stream, guys, is on Tuesday at 6:30 p.m. GMT +1. Yeah. Wait a minute, I need to jam back here. Raid. Feel free to... Wait, slash raid, isn't it? What a moron I am. Wait. Yes. Yeah, feel free to join the Discord, come hang out, and yeah, have a good start to your week, your work week, and whatever it is. And yeah, I'll see you on a future one. Wait, let's reply quick. What are people saying? Oh, thank you guys. Yeah, it's really cool. Yeah. Right. Awesome. See you later. Catch you later. Bye.